matter and so on. That is
That's
what you
right.
are.
That's right. And you know, the universe seems to be asymmetric, right?
I see. Okay.
Anyway, yeah, I'm quite interested in this. So if you have some ideas, that will be super interesting for me.
Uh, I don't know what I had in mind right now is something like do you know the atom key experiment? Uh, there are some
Uh-huh.
people claiming that there is a kind of new very light boson, the X17 or something like this.
Yeah. I
And
think it's no longer, as far as I understand, it hasn't been confirmed, unfortunately.
uh,
would
uh,
have been would have been fun, but I
uh,
don't think it is.
I don't know. This is what I heard, but I think a Vietnamese group
Uh-huh.
did also. They claim that they confirmed this
Oh, no,
X17.
that I haven't
I don't
heard.
know whether it is really okay, but at least there are two groups claiming that
Hello?
there is this kind of resonance part, helium, blah blah. So
Interesting.
I don't know. Maybe it is one opportunity. I don't know. Yeah. So sorry, I will not disturb you further. I think
Not at all.
we have to start the
Yeah, we'll
session.
talk more about this. I mean, okay, so maybe we can start, and I'm sure others will join as the meeting progresses. All right, so I'll not take too long. So first of all, let me welcome all of you to this important event. And this event is to celebrate Professor Dmitry Budker's 60th birth year, I should say. And I mean, I've known him for a long time, so it's hard to believe that he's 60. But I think many of you know. I mean, I see some names that I don't recognize, but they must all be very young. But I would like to say that Professor Dmitry Budker, I mean, we all call him as Dima, is one of the greatest experimental, atomic molecular optical physicists of our time. And, as you probably must have gathered from the short conversation he had with Dr. Yamanaka, he, in addition to being a great experimental physicist, he's also very curious about scientific things and also things about society, about different countries, and extremely compassionate. So, he has all of these outstanding qualities, and which is what makes him an incomparable scientist. Now, I will, I'm sure, some of you know about his important scientific contributions, which are many. But I just want to say a few things about his association with India. So during one of my visits to University of California, Berkeley, exactly 21 years ago, in a conversation with Professor Budker about problems of common interest, particularly parity violation in atoms, he suggested that we could have a US-India joint project, and the idea appealed to me. So we looked at possible sources of funding, and we found that NSF, USA, and DST, the Department of Science and Technology, Government of India, that they had an exchange program, so we applied, and we were successful. And so Professor Bhutkar visited us in India. That was exactly 18 years ago. I mean, November 2005. I mean, and so I was delighted, and so I decided to have an AMO, Atomic Molecular Optical Physics meeting, in which we invited scientists from Raman Research Institute in Bangalore and also Indian Institute of Science. And it was sort of a symposium. And there were many interesting talks, including Professor Bhutkar's. Then we had arranged his visits to both Raman Research Institute and Indian Institute of Science. I mean, as I said, he's very curious, he's very interested in knowing about different things. So he hit it off with scientists in Raman Research Institute, particularly Professor Sadiq Rangwala, who will give the first talk today. And, so the collaboration was no longer just experiment from the US and theory from India, but it also included experiments from India. And Orijit, who's going to give a talk today, he has visited Berkeley and was a postdoctoral fellow with Professor Bhutkar in Mainz. You'll hear all about that. So that was in 2005, and of course, during that visit, he also went to a physical research laboratory in Ahmedabad, and Dilip Angom, who's also going to give a talk. I mean, he I'm sure will be happy to recount some of those experiences, and so I'm not going to say anything about that. So after that, the next visit, I think, was in the beginning of 2010, or could have been end of 2009, beginning of 2010, and that is when he went to Delhi, Mumbai, and Kolkata, where we had an atomic physics conference, cold atoms and other things. And that, I think, was a very interesting visit in which Dima, who had come with, I think, his oldest son, Andrew, and a student, Simon. They also did some sightseeing, probably went to Taj Mahal as well. And then they went to Mumbai, where they, I think Dima took part in a laser symposium. and then to Kolkata, where he gave an outstanding talk on atomic parity violation, some recent results of one of his experiments. And after that, in 2013, I think beginning of 2013, Vijay Sahu, who will join, I think, very soon, he and some others had organized a workshop on CP violation in Mahabaleshwar that was supported by ICTS. And that is when, he talked about, I think, axionic dark matter, I suppose. And so that was in 2013. And then 10 years later, after moving to Germany, he had visited us again this year in July. And that again was an ICTS sponsored conference on topics at the cutting edge of atomic and molecular and optical physics. And and I made a special effort to attend that conference, primarily because, Dima was attending it. I had not seen him for a few years. So I thought I have to go, and I'm really happy that I did. And so you see, he has visited India many times and probably has observed many more things about India than you and I have, So I'm not going to say too much about it, but that's the way he is. He is very curious about things, not just about science, but about people, society at large. So, and I should also say that many scientists from India have visited Berkeley, Mainz. People have done postdocs with him, and he undoubtedly has been a great source of inspiration to many of us. As a theorist, I can say that with certainty, and I think many experimentalists probably will echo my views. And I mentioned in the beginning that he's one of the greatest experimental AMO physicists for time, but he's much more than that. He does physics, outstanding physics he does, but he combines that with compassion, understanding, and that's what makes him quite different from many scientists, at least the scientists that I know. And so I am sure that many younger scientists would be interested in interacting with him, collaborating with him. I know that a colleague of mine, Tonmoy, who actually helped me organize this the symposium, is very, very interested in having discussions with Professor Bootker, and I'm sure many of you are. So that's all that I wanted to say, and as we go along, you'll get to know Professor Bootker better, and I'm sure in the future we'll have very productive interactions and collaborations with him. So, Dima, so once again, congratulations on your 60th birth year, and we look forward to, many, many more years of, very productive and fruitful interactions and collaborations with you. Okay. Thank you. Okay. All right. Okay. Yeah. All right. So with that, we can start the talks. So the first speaker is Professor Sadiq Rangwala from the Raman Research Institute.
So should I start?
Yes, please.
Okay, thank you very much. It was a very wonderful and emotional introduction to this meeting, and I'm honored to be the first speaker in this meeting. Hello, Dima. I join everyone in wishing you happy 60th birthday. I am sorry I could not make it to your 60th birthday, but there were certain very peculiar circumstances which arose, which had to be handled locally, and my time got shattered in that period. In any event, I'm super happy to have this occasion to rectify that that loss for me. And from all accounts, which I got by emails, it was something. I do hope that this is to your expectations. This meeting is to your expectations, and I thank Professor V.P. Das for arranging it. because it is actually this. So I'll just preface my talk with a few words and then move on to the technical part of the talk. And the thing is that it is actually my involvement with Professor Budkar, DIMA, was quite long. It has spanned many years. And there was a very active period where we published several papers together. And then there was a lull, which I hope we can overcome in the near future and do some good work again together. Meanwhile, there is, of course, a lot of convergence of interest. It has always been there. And what I would like to say is that Professor Bhanudas has very generously, in that period of time when DIMA was visiting, essentially opened up the possibilities for interactions with a vast number of researchers, particularly in the Bangalore area. And DIMA gave his legendary endless talk at RRI, which he recalls even to this day. And that was quite an interesting experience for everyone. And the outcome was that we all started talking, and one thing led to another, and we did a lot of work together. And I then subsequently visited DIMA on the grant, which was talked about by Professor Bhanudas and earlier. And so that I spent, I think, 40-50 days in Berkeley, where we again did experiments. And then people came over from Berkeley to do experiments in our labs. And Arijit Sharma, who has joined here for this meeting, is also somebody who was deeply entangled by DIMA in many ways. So it's a nice little circularity which we have. And with that, I would like to start my talk. Is that how much time do I have for the talk? Can I start?
Yeah, it's 40 plus 5.
Okay. So what I'll do is I will just wait for a signal from someone at 30 minutes.
Yeah, I will do that. Yeah.
Okay. So then I will get with the talk, and so fantastic. Can you see my screen? All right. So I hope my screen is visible to everyone. I'm going to hide myself. So I tried to open the Zoom meeting on another screen, but I'm unable to do so for whatever reason. In any case, I will keep it in. Yeah. So what I'm going to talk about is spectroscopy and measurements with optical cavities. And this is a long program. And I would say in some way, what I'm going to do in this talk is kind of, completes a circle with work which was started with DIMA. So at the time that when I went, okay, so here's a very recent picture from his from his visit earlier this year, where we met up. This was when he was lecturing at ICTS. And it was a wonderful time to meet up and get in touch again after a while. So what I'm going to do in this particular talk is I'm going to talk to you about physics with cavities, and you will see that a lot of the cavity work is now around molecules. And the first time I ever used cavities as an experimentalist, apart from actually using it in a laser, was to do molecule spectroscopy with DIMA and his student Victor. And we were doing those things, and they had come to the Raman Institute with a box of stuff, and we set it all up together, and we did some spectroscopy and had a lot of fun in the process. And that brought out possibilities for doing work with cavities. That cavity program was started by Arijit at RRI, and you will see the experiment that he built, which I'm going to talk about, and I'm going to talk about some results from that experiments today. Some of it, the initial introductory part, are his own results because he has measured them, and he is an author on those papers also. And then subsequently we will move on to what we can do with cavities and molecules, and how we can do very funky things with cavities. So that is essentially the structure, if you can call it that, of this particular talk. It's kind of nostalgic, but I chose these topics because they connect well with how we started with DIMA. So, so just a second, let me organize my screen a bit. Yeah. Okay. Oops, sorry. So one of the particular and very important aspects of working with cavities is that when you want to make a detection in physics, you want to you are looking for a signal, and the signal normally that you measure is some light or some amplitude essentially comes your way, and your measuring instruments pick it up, and you get a certain, the size of the deflection essentially gives you the measure of the signal. However, such a signal is, while it is extremely happy, we are all very happy to have a good signal, such a signal is measures a certain level of intensity or amplitude or whatever, and then you make your inferences. There's an even better way to measure signals. If you can convert that signal of whatever the system is telling you into a frequency-dependent signal. Frequencies have the virtue of being much easier to measure than amplitudes, because for amplitude measure, I mean, it's just an easier way to get to measure a difference in frequency is way more precise than to keep track of an amplitude over a long period of time. And that is essentially at the heart of this way of doing measurements. And I will show you why what role cavities play in getting this signal. Oops, excuse me. So if you're going to detect light, then your signal is something which is due to scattering, and they will give you an intensity signature. But if you want to now start detecting interactions between atoms and molecules with light, then you can convert this interaction signature into a frequency measurement, and various nice possibilities opens up, and I will definitely show you a couple of such examples today. Okay, so if you have, for instance, and this is a problem I will talk about, if you have a dilute ensemble of molecules, they're much harder to detect spectroscopically and through light scattering alone. So can we find alternative ways of doing detecting dilute ensembles of molecules? So in order to do this, what do? We need to convert the interaction of a single mode of light with an atom and generate a frequency signature of that interaction. And that is via atom cavity strong coupling. So what is this thing? So if you have n atoms in a certain volume, okay, then what you need, you can write the Hamiltonian in the form as, can you see my mouse here? Hello?
Yes.
Yeah, I'm just trying to see if I can get a laser pointer up. Well, forget it. So if everybody can see my mouse, that should be good for the moment. So you have an amplitude, which is here. And essentially what you have is, in this amplitude is the term for the atomic state, the term for the light mode, and this term, which is the atom field interaction. And essentially what that does is, if you say that the detuning between the light and the atomic transition is actually 0, then what you would get is the frequency, the effective frequency, which shifts from the light intensity omega by when the atom field interactions is on, by a factor which is g, which is just a number which relies on the atom coupling to the mode, and the square root of the number of atoms coupled to the mode. And so for a single atom coupled to the cavity, the frequency difference between the plus and the minus is essentially 2g. And this is extremely helpful paradigm in order to convert atom-photon interactions. The measurement of atom-photon interaction is now something that can be spectroscopically given by measuring a shift in the intensity of light, which is in the mode of the cavity. Okay, and so if you now have n atoms, then essentially what you get is 2g0 as the square root of n, which is the transmission frequency split for n atoms in a cavity. So this is one of the things which the very standard results. These are from Travis and Cummins in 1969, and then G.S. Agarwal has a very lovely paper from 1984. These are classics, and this is essentially at the heart. This is at the heart of the scheme for detection that I'm going to talk about. Just a minute. Something. Okay. So now let us move on and see what more we can do with this system. So what is the motivation? As I said, the motivation is to detect the fluorescence signal, and absorption techniques have their own peculiar, they are very strong techniques for detection of matter in certain regimes. But as you can see from my previous slide, because you can scale from even one atom to several, in fact, tens and thousands of atoms, and even maybe close to 1 million atoms, you can actually, you have a vast range of possibilities in a cavity, which is very nice, starting from a single atom. But anyway, the point is, cold atoms are easy to detect. Okay, if you have an ensemble of laser cooled atoms, they are easy to detect by fluorescence and absorption techniques. However, for cold molecules, it is not so simple, because molecules have a large number of rotational and vibrational states, so they're not laser cooled in very effective ways. There are some recent experimental techniques which allow for fluorescence, which allow laser cooling of molecules of certain kinds, and they are extremely breakout. They're very important experiments. But on the other hand, there is also this large fraction of molecules for which it will not work, particularly the alkali atom molecules. These techniques are not that they work for radicals at some level. Okay, so sorry, for whatever reason. So what we now require is that optical detection efficiencies need to increase dramatically for cold molecules. And what we do, and what I and my group have done for a very long time, is construct hybrid traps, which can simultaneously trap more than one species. Okay, so for instance, atoms, molecules, ions, and light, and I will show you an example of that. So we are well poised to start trying to do molecule detections using atoms and cavities. So we will leverage the atom cavity coupling, strong coupling, to do various kinds of detections. Okay, so what are the problems with this technique? The main problem is that cavity techniques work very well with a two-level atom and a dipole allowed transition. For real atoms, they are multi-level, and multi-level atoms have multiple transitions which are simultaneously possible. Now, if you have multi-level atoms, the other levels, so the cavity is a tuned resonator which is set to couple to the resonance of the two-level atom system. But when you have multi-level and other transitions become possible, you have losses from this multi-level, from the two-level system, and that is very detrimental to cavity, probing atoms to cavity, and the signal is lost. This frequency signal that I was talking about is lost. So what you want to do is study atoms and molecules in this lossy limit and figure out how to get cavity-based detection systems to work. So this is our experiment. This is a trap, which is, if you want an all-in-one trap, it traps atoms, ions, molecules, and light in whichever combination you want. Okay, and it can trap ions and molecular ions also. Okay, so I will just take you through what the experiment looks like. You have a vacuum system. You have cavity mirrors, which will define the mode in which you are going to do all the probing of the atoms. This is the cavity piezo. This allows you to set the length of the cavity so that you can tune the resonant frequency with which the light in the mode and the atoms would couple. You have the Mott beams, which can make the cold atoms. You have a charge particle detector, which can collect the ions which are created, and you do experiments with. This is the core of the experiment, where you have the two blue wires, which are the spherical Paul trap radio frequency electrodes. Then you have linear Paul trap electrodes and extraction. These can be then you have these 4 quadrupole rods, which are either electrodes which you can use for a linear Paul trap, or you can use them for extraction. And you have this red electrodes, which are the end cap. So either you use the end cap electrodes and the linear Paul trap, the 4 rods, or you use the 2 blue wires and put a radio frequency on them, and you use the red wires as the end cap trap. And these two give you different kinds of ion traps. And this is our system. And all of this is happening inside a Fabry-Perot cavity. So the red is the trapped atoms, which is a very small volume. And the gray area is the volume for stable ion trapping. And what I must tell you is that Arjit Sharma, who is here in the audience, is one of the 2 key members who have fabricated this experiment. The other is Tridib Ray. Okay. And so now how does atom cavity coupling work? You have a two-level atom inside a cavity, and this couples to the mode of the cavity with coupling constant G0. Then you have the ability, if you are in the excited state and you drop a photon out of the cavity because of spontaneous emission, you have a line with gamma. And so gamma will give you the rate of photo emission. And there's the kappa, which is a leak of light from the cavity. So these are the loss channels. The gamma and kappa are the loss channels. And if you want single atom cavity coupling condition, the strong coupling condition, G0 has to be greater than kappa and gamma, where G0 is given by the dipole matrix element and the frequency, the transition frequency in the cavity mode volume. In our system, when it was constructed and even now, G0 is much, much less than gamma and kappa. So our cavity coupling to the atoms is weaker than the rate at which light is exiting from the cavity through gamma and kappa processes. So single atom strong coupling is not possible is basically not happening in our system. So, but we get collective strong coupling, and a few thousand atoms is enough to see the strong coupling signatures. And I will show you data on this as we go. So single atom vacuum Rabi splitting is essentially goes like this. This is if you have a ground state atom and n photons, then this is the hierarchy of energy levels that you have, where you have different ground state atoms and different photon numbers, creating a ladder of states. Or you have excited state atoms and n photons and a ladder of states. Now, when they interact, then there's a splitting in the levels, and what you get is a superposition of the excited atom and 0 photon, ground state atom and 1 photon, and so on and so forth. And you get a splitting in energy levels because this degeneracy is lifted by the perturbation term of the atom photon interaction, and we get we get the lifting of the degeneracy. The measure of this frequency is essentially the atom cavity coupling. It's a direct measure of this term. So how does this work? N atom coupled to a cavity. So you have n atoms in a cavity. Here's your mode. And what can happen is, why does strong coupling work? Strong coupling means that a photon which is emitted by an atom here will hit the mirror and get reabsorbed by another atom in a different location. So if it's a single atom strong coupled to the cavity, the atom will absorb and re-emit the photon. But here there are multiple options which allow you to, because there are many atoms in the mode. So you can get that is what gives you the NC term, and that gives you the square root of, that gives you the atom collective strong coupling term, which is Gn as G0 square root of NC. So this is what it is. Now let's look at how the experiments are done. So this is a very old experiment where you have a magneto-optical trap centered in the cavity, and here is what you would get if your cavity was empty, the black dotted line. The red lines are essentially when you have collective strong coupling of a certain number of atoms, and you can see that this has cleanly split this, the transmission, the atom cavity resonance is now split into two parts when the cavity is loaded with atoms, and this is the measure of the intensity. Here it's about 75 or 80 megahertz. So this is a thing, and what you can do, and this was an important thing that we did, and this is that what is usually done in cavity physics is that you use the f is equal to 3 to f is equal to 4 prime. Basically, you use a closed transition so that an atom in f is equal to 4 prime can only radiate by dipole selection rules to the f is equal to 3. It cannot radiate to f is equal to 2. So this is available for repeated cycling. However, what we did is we could show that if you add a little bit of repumping light while probing the atoms to the cavity, the atom cavity system, we could have excellent results for the open transitions. And this was actually a very important step. And this is one of the things which opens up the atom cavity system as a versatile detector. And here you can see that we are doing it not only with the closed transition, the 3 to 4 prime, but with the open transition too, we are seeing the strong coupling split of the two peaks. And if you are wondering why the splits are different, that's because the coupling, the coupling between the various levels are essentially different, and that scales the G naught. Okay, so this is what happens, and here's what, okay, I will not spend time on this thing, but I will just skip over this slide and the next slide, because it just meant to show you that it works for all the transitions, and we can, for a simple atom like an alkali atom, we can effectively enhance the potential of this of the atom by measuring on the open transitions. And let's not worry about this. This is a temperature measurement, and I'm going to skip this. So now let's get to molecules, because the slide I just skipped was just a summary of what I've just told you. So now a molecule is a very interesting system. And as I told you earlier, that the atoms, when you have an open transition, it is very difficult to see the atom cavity coupling in a cavity system. Now, and an atom, like an alkali atom, is only a few levels. A molecule has thousands and thousands of levels. And here's an illustration of a molecule. And you can see that you have the electronic state, and you have some vibrational levels, and you have, within this, you'll have a rotational manifold, you will have hyperfine splits, etc. So the density of atomic states is very large. So here is a kind of a view of the rotational levels, etc. within the vibrational manifold on the electronic states. So you can see that this is very complicated. And now what we are talking about is something which has so many levels that we got to find a better way of doing everything. So is this task hopeless, is the question. Okay, because you can see that you have, in a harmonic oscillator potential, you can only go to plus minus h cross omega through a dipole allowed transition. But in an anharmonic oscillator, that is not true already. Okay. So further, there are rotational, but what you find is there's something which is very interesting, which is the rotational levels, which correspond to the rotational degrees of freedom of the molecules. They have very tight selection rules. So while in a molecule, the vibrational selection rule becomes weaker, the rotational selection rules are very strong. And that actually seriously limits how many levels you can actually drop down to from an excited molecule. And also, if your molecule is something which is a very good example of the Born-Oppenheimer approximation, then Frank-Condon overlap integral dominates the transition scene. And so the essential thing is that it is not a hopeless task to even try and do direct detection of atoms or of molecules with cavities, because finally there are not as many levels as you might think that participate in the process in general. So we did a little bit of theory. We wanted to really figure out whether it is still possible, even if the levels are kind of limited, whether it is still possible to do this. And we looked at it from a vacuum-Rabi splitting paradigm and an EIT paradigm. So the vacuum-Rabi splitting paradigm is that all of the blue light, which is what is not returning back to the level you use to probe, is essentially considered as a loss. And the question is, can you actually devise a cavity-based system to overcome this loss and try and find the and try and measure molecules directly using the techniques I just shown you. And well, it can be done. And this actually is a very neat way. So what you essentially have to do, what it shows you is that you have to ramp across the transition.
Excuse me, we have about,
yes.
About 8 to 9 minutes left. Okay, sorry.
Okay. All right. So fine. So let me cut this short. So what we showed in this theory paper, that it is actually a possibility, but the cavity we have right now is not configured for this. It requires a different kind of cavity. And we worked on the EIT problem too. And the EIT problem also, we have worked on analogs of these two problems with atomic systems. And we have tried to see whether these will translate well into the molecular paradigm. And we find that the EIT does not translate very well, though it is very promising from a theoretical point of view. And I'm not going to present those results here, but it's something that we are writing up. The EIT does not translate well for certain technical reasons, which I can discuss later. But the VRS, the vacuum-Rabi splitting, still works out very well. And so we will push on the vacuum-Rabi splitting. And now let me show you how we do molecule detections with our present cavity. So there's a process called photoassociation with cold atoms, where you have basically two atoms which are free, and a resonant photon is incident on them, and they form a molecule, a bound state, long bond molecule. Actually, if you look at it from a spectroscopic perspective, these are the ground state potential energy curves of rubidium. These are the excited state energy curves of rubidium. And what you do is you put a laser between, which will connect the free states of these atoms to a bound state. And when you see, you get so if you look at this is trap loss. So you have a normalized intensity, and as you hit a resonance, you find that the atoms deplete. These depleted atoms are actually forming molecules in the excited state. Now, these excited molecules can decay back into free atoms, and actually that doesn't happen all that often. Or it can come down into the molecular ion, the bound molecular state. And this is something which is ongoing. Photoassociation is something which has been around for a very long time. I think the first experiments were in the late 80s, soon after the magneto-optical trap was developed. So now here is what we are doing. So now we wanted to use the vacuum Rabi splitting technique that I've just talked about in order to tell you about, to detect the formation of excited state molecules. So now we have a magneto-optical trap. A magneto-optical trap, for those of you who have seen it or seen pictures of it, is a ball of atoms which is fluorescing. So you can detect the fluorescence, and this is what we are doing. But however, while we are detecting the fluorescence, so here is, we are also making sure that it is coupled to the cavity, and we are essentially measuring the vacuum Rabi splitting on an open transition, okay, like I showed you earlier, on this in the cavity mode. And so here is the bright MOT, and here is the loading if it is off resonance of the MOT, and here is the loading of the MOT when it is on resonance. So by on resonance, what I mean is it is sitting, you're sitting somewhere here, okay? So all of this is done actually on PA5. So somewhere here is on resonance, somewhere here would be off resonance, where there is basically no depletion of atoms as a function of frequency. All right, and you can see that this is the loading rate which is measured, and here are the numbers for the bright MOT fluorescence signal and the fluorescence signal with PA. Now you can do the same experiment with the VRS, and you can then detect, and you can see that you can measure very nicely within the error bars the same values of the loading rates and the loss rates of the MOTs. So essentially what we are showing you here is that the MOT, whether you are measuring it through fluorescence and the molecule formation process, whether you're measuring it through fluorescence or whether you are measuring it through the cavity mode, they're giving you pretty much the same thing. So now what we do is something which is extremely hard to do in a regular experiment, which is if you are in a dipole trap or if you are in a dark mode, then you do not have the fluorescence signal available to you. And now the question is, now that we have shown that the bright MOT, the fluorescence signal with the cavity is equivalent to the fluorescence signal, to the cavity mode detection signals, we can now use the cavity mode detection to detect when the MOT is dark, which is that it is no longer in a fluorescing state, and measure the photo association through this process by looking at the vacuum Rabi splitting. And here are splits on each of these 6 peak at some intermediate values of photo association intensity. And essentially what you see is that, so you can measure it very nicely. Here is the MOT which is off resonance, and here is the MOT on resonance of the PA, and you can see that you are measuring the completely different rates. And this is true because now the density distribution of the cold atoms is very different, and the number of atoms you can load in the MOT is different, and so on and so forth. So this is expected. One of the really nice things is that we can do these measurements continuously. Each of these points is done at an interval of something like a few hundred microseconds is the time between the points. And the other very interesting thing is that when you do photo association with a bright MOT and you look at the fluorescence dip to measure the signal, typically you will never ever get a signal which is more than 50 or 40% depletion of the atoms. So less atoms get converted into molecules in a bright mode than a dark mode, and that is just because the dark mode is completely optically pumped, and it's starting, all the atoms are in a single state, which is in the non-fluorescing cycle. So it works very well. You have a much higher efficiency of producing molecules with the dark mode. We can do these measurements continuously. I mean, we at few hundred microseconds, and we can improve it further. These measurements on the molecular resonances are non-destructive because we are actually measuring the atoms which did not participate. So while this is giving us an excellent example of a non-destructive measurement where you are the atoms which are not part of the molecular ensemble are being measured, and the molecular ensemble is being measured with great accuracy. So this is how we are going forward at this particular point of time. I think I'm out of time, so I will leave the how to make a laser out of atoms out. I will leave that thing out, and I will want to show you some of the heroes of this particular experiment. Gokul is the one who has led this experiment, the Arun. There is Vardhan and Shreyas. These are the guys who have actually worked on these experiments and made various experiments possible with cavities, and they're doing phenomenally well now. And we have a lot of excellent, very exciting results which are going to come out from the cavity experiments, and it's thanks to them. There's, of course, the earlier work of Arjit, Tridib, Jyoti, Saurav, Rahul, which has been instrumental in taking these things to where they are right now, so that we can build on a decade of work and go into completely new domains. So with that, I say thank you for your attention, and I'm open to questions.
Okay, so thank you very much, Sadiq. And any questions, comments?
Sadiq, thank you so much for great talk. Very, very interesting. Just a question on terminology. Spherical Paul trap means that the potential it has spherical symmetry, right? Because your wires are nowhere close to spherical, right? They are.
Yeah. So okay, so the thing is so it's more like the classical Paul trap. Can you see me?
Yes.
Okay, so if you imagine the classical Paul traps, you had two parabolas. Actually, it was essentially there were hyperbolas, two hyperbolas, and a torus, which was hyperboloid. I mean, and the idea is that you make the lines of the equipotentials have a certain structure which gives you a harmonic trap at the center. Now, what happens when you put a wire or something very irregular is that over about the dimension of the wire, the potentials tend to heal. Okay, so about a couple of wire diameters away, you have already started healing to an extent that your potentials take on the aspect of the idealized potentials. And so you don't have to spend a lot of time, grinding your electrodes into perfect shapes which coincide with the equipotentials. So long as your electrodes are far away enough to give you the healing of the potential, you are quite good. And therefore, what I called as a spherical Paul trap is essentially a torus, okay, which is the RF and the two end caps, and it will heal into the potential in the very center of a regular of the idealized Paul trap, which you would see in a textbook.
Thank you. Yeah. May I ask another quick question?
Yes, of course. Yes, please.
So when you do photo association in the trap takes the momentum, right? So it's like another body, effectively.
Well, the photo association laser is actually coming from the side.
Mm.
Okay, we are not photo associating with the cavity mode.
I mean, not the cavity, the trap.
Yeah, okay. So there is so what you're saying is that there's a recoil.
Yeah. And you need to take it somewhere, right?
Yeah, that is the trap is so now if you're asking me whether the magnetic fields which are tied to the earth take the trap or take the recoil, or the lasers which take the recoil, I wouldn't be able to answer that super clearly. Okay, but yes, of course, we need to conserve Mr. Momentum.
Yeah.
But those are very small. So the thing is that the momentum recoil of the atom is of the system is super small. And as you know, if you're going to do laser cooling of atoms from, let's say, a room temperature vapor to 100 microkelvin or less, you need several 10,000 momentum collisions in order to effect that. So these experiments do not have the resolution. In fact, actually, the experiment which had this resolution was and this will interest you because I saw it at Lawrence Berkeley National Labs when I visited you. So there is this experiment with sodium, radioactive sodium, where I forget the name of this person. He was doing it through a hole in the wall. So the sodium 2022.
Probably it was Paul Vetter in Stuart.
Yes, Paul Vetter. Paul Vetter. Yeah. Exactly. So he was doing an experiment with sodium 22. Sodium 23 is the naturally occurring isotope. 22 is very highly radioactive. And he was, so from a hole in the wall through some stuff which is in the background would come a beam of sodium 22, which he would then make a molecule out of, and that would undergo a beta decay. And the idea of that was to using the recoil to determine the neutrino, to do recoil physics and essentially try and pin down the mass of the neutrino if possible. And the trouble in that experiment was actually sodium is a very bad system to go with because there is all sorts of molecular processes that are going on in sodium. So the biggest background was the uncertainty due to the molecules which were being created, okay, in that experiment. Because if you make a sodium mort, you are anyway creating molecules also, all the time. And therefore, the momentum signatures were getting smudged. At least that is when Paul Vetter, when I was talking to Paul Vetter, that was the problem. I do not know how it has been resolved since, but so yes, it is a problem. And but in this particular case, it is not significant.
Thank you so much.
Okay, so thank you very much, Sadiq, for a very novel talk and interesting results. And so now we'll move on to the next speaker, that is Professor Bijay Sahu.
Thank you. So can you hear me?
Yes, yes, yes.
Sorry, I cannot switch on my video because my camera is not working, so you may not be able to see me. And also, I'm sorry that I attended. I joined this meeting little late because I'm attending currently another meeting. Okay, so let me share my screen. Okay, so you are able to see my screen?
Yes, yes.
Okay, so I just put it in full screen mode. So, okay, so let me first thank Professor Das for, giving me this opportunity to, speak here in the honor of Professor, Dimit Budkar, to whom I consider as a very good teacher and a good mentor and a very good human being, actually. That is the most important, this one. The topic I'll be talking about is, just let me hide that, this thing where, okay, it's gone. So a roadmap towards, CGM parity violation study from theoretical perspective. Before I move to my talk, I would like to give a very small tribute, in my personal capacity to Professor Budkar for his 60th birthday, to whom I wish very good health and prosperity, and many like so I would like to see him actually as it is for the many years to come. So my association with him is a lot, though on the record that may not be visible, but he was one of my thesis examiners, PhD thesis examiners, and he's always a very well wisher of mine. He has provided recognition letters for my postdocs, for all my jobs, promotions, and he's really a real role model for my research work. I was very fortunate to have only one publication that was in 2010 with him, and that was actually my first publication after joining in PRL. But indirectly, I have benefited from his research work a lot. Like, for example, whenever I have written papers on this atomic parity violation, like after joining PRL. So here you see in 2011, I had written 2 papers. So there I had cited his work. It was in the introduction itself. And in the latter part, also in the recent years, whenever I write papers on parity violations, there I have cited several of his papers. Actually, I'm following those papers and they're not just cited. And below you can see also a couple of papers where we have cited many of his papers, but it's not because of lack of space, I have not mentioned them explicitly. And I really follow all of his other works on actions and other things, which I have not mentioned because I am not directly working on that currently. But I do have plan for working those things. So all those works, actually, his works motivate me to do this kind of a research. So with this brief remarks, I'd like to now move on to my the talk. So the outline of my talk would be like just I'll give a general introduction to atomic parity violation, and this is one of the major research work of Professor Budkar, who has set up one experiment on ytterbium atom, and I think later we'll have more talks on this. And but I'll be talking about the APV study in CGM and why it is important, and the role of many-body methods. Then the first principle approach that we have applied to study this APV in CGM. Then we'll compare the results with previous studies and we'll give you the new findings. And then there was some debate on the disagreement of our results with others, whether that is a disagreement or agreement, that we'll find out towards the end of this talk. Then I'll also suggest a few way of for going forward before summarizing and giving outlook of our work. So as you know that in particle physics, standard model of is considered as treated as very standard, like a very well accepted model that predicts three fundamental forces, and in fact deals with three fundamental forces. And it describes 12 fundamental fermions, 12 gauge bosons, and the most important outcome of this model is it gives us parity violation. And then it also explains CP and time reversal violations. It unifies two fundamental interactions like weak interaction and electromagnetic interactions. And it says that CPT is conserved. But in the right hand side, in the red color, what you see that these are some kind of open questions that standard model is not able to address, like why there should be only three generations of quarks, and why we see more matter than antimatter today, and then why neutrino has mass, why there are like even we have observed some signature of dark matter or dark energy. So those physics are not able to be explained by the standard model of particle physics. So that is what we are trying to see this kind of physics, but because of which people have proposed many other models in particle physics, and one of the models is supersymmetry models, which predicts there are symmetric particles of standard models. Like if you have some kind of fermionic particle, fundamental particles in standard model, you will have here the corresponding bosonic particles and so on. So because of these new kind of particles, you will also expect new kind of interactions, and also new kind of exchange particles and so on, that can give rise to different kind of coupling strength due to the interactions of these particles. And this kind of like phenomena one can directly see using high energy physics studies, using certain kind of facilities. But what we are trying to do here is how to see some of these signatures at the atomic level, that is by performing low energy scale experiments, or also low theory performing the atomic calculations. So here, what's the novelty? Novelty is we have to complement high energy physics probes using low energy experiments. But then question is why atoms? Now, if you see this picture, this cartoon, so the size of atom is almost like it's a much bigger than the fundamental particles. We can talk about like electron or quark. So the size is, though it mentions as 10⁻⁻16 or something like that, but it's much smaller than that. That the size of electrons and quarks. So the idea is the kind of, if you want to understand the nature of interactions of electrons or quarks, whether we can indirectly inform them from the atomic studies. Okay, so that means we would like to consider atoms or molecules as proxies to infer some signatures of this kind of fundamental particles, like size of electrons or size of quarks, or the interactions among them. So like if you want to go from quark to proton or proton to nucleus, the size increases and the atom is considerably larger. Now, if you follow this Heisenberg's uncertainty principle, so if the size of the particle is like very small, so you need very high energetic experiment to observe them. But if the system is very large, so you need actually low energy kind of technique to observe them. So that is the idea. Now, if you see here, the kind of the facilities people use in the high energy probe, that is CERN, the LHC kind of facility in CERN, Geneva. So you see the size, compared to one human being, which is standing in the middle. And then in the right hand side, you see the kind of experimental facilities people are using. This is a facility from Professor Budker's group from Mainz. Though I have not visited him, but I have taken from his homepage this picture. So this is the kind of facility one uses to this probe this low energy probe of fundamental particle physics. Okay, so the the problem that I'm going to discuss is the atomic parity violation, and to probe BSM physics using this atomic parity violation. So how atomic parity violation occurs in the atomic systems. Now, if you consider these interactions between electron and nucleus, atomic nucleus. So basically, we usually consider the photon as the intermediate particles, like that gives us electromagnetic interactions. But apart from that, so there are also some interactions we neglect, that is due to the exchange of Z0 boson that gives us weak interaction that is predicted by standard model of particle physics. And if you go beyond standard model of particle physics, like supersymmetry or something like that, so that also predicts some other kind of like ZX boson or ZD boson, like they are called extra Z boson or dark boson or something like that. And due to exchange of those particles, so we can also see some kind of weak interactions happening within the atomic systems. Now, our the problem of interest in the particle physics to find out the coupling coefficient between electron and a quarks, that is up quark or down quark, and their values are given in the right hand side using in terms of Weinberg's angle sin square theta w, and these values are known to 0.5% accuracy in the standard model of particle physics. Now, the idea is if we can find out some quantities that basically, that is written as a linear combination of these coupling coefficients of up quark and down quark with, electrons, and that is known as weak charge, nuclear weak charge. And that, so for each atom, then they are coherently added depending on the number of protons or quarks we have in the system and, electrons. So these values are known, nuclear weak charge values are known very precisely. So let's say if we can infer this quantity from the atomic studies and compare with the values that are given by standard model, and if we see some deviation, and from that deviation, we can actually infer some kind of signatures that can be predicted by other models of particle physics. So that is the idea. So there could be some small corrections due to the radiative corrections, but most of the contributions to this deviation may come from beyond standard model, which we call BSA. And if we see that kind of delta Q, whatever I have written, so that is the anticipated deviation one could see from the standard model particle physics. And if we can find out this delta QW, so from there we can find out that whether this ZX can contribute and give us that kind of deviation, or this ZD particle can give us that kind of deviation, or because the sin square theta W value, that is Weinberg angle, that differs, that is like, that is something like whatever is known by standard model, if it differs from that, so there could be some deviation in that. So this is basically the objective of studying atomic parity violation. Basically, we are trying to find out this QW value as model independent quantity, and from this atomic, by combining atomic experiment and atomic theoretical studies calculations, and then we would like to compare with the standard model value. So that is basically the objective. And if you see the deviation, so that deviation will be very meaningful for us. Now, again, when you talk about this electron nucleus interactions, and if you remember in the weak interaction, so weak interaction happens due to the axial vector current kind of interactions or vector axial current kind of interactions. So here we have two different kind of particles. One is electron, another is nucleus, which consists of quarks. And then that means this axial vector current can come from the electron side or from nucleus side. Depending on that, we'll have two different kind of interactions. One will depend on nucleus spin, and another one will depend, will be independent of nucleus spin. So nucleus spin independent contribution is what that corresponding coefficients are written as C1Q, means Q could be up quark or down quark. And for nucleus spin dependent, we denote the coefficient as C2. So here basically we'll be interested right now for the current presentation. So we'll be interested only for NSI kind of interaction, nucleus spin independent kind of interactions. But Professor Butker's the PNC experiment, actually it's more interested towards finding out NST kind of interactions. But then there is another kind of source will contribute there, that is the nuclear unupole moment. So that's beyond the scope of this talk. So I'm not going to talk about that here. So I'll be focusing more only on the nucleus spin independent kind of component. But as I said, these C1Q coefficients are known very precisely to 0.5% in the standard model value. So to inform these coefficients from this atomic study, so we have to also carry out these atomic experiments and atomic theoretical calculations to less than 0.5% accuracy. So that is the challenge. Now, this the behavior of the weak interactions atomic system goes like that. It basically happens due to the mediated by Z0 boson, or could be some other kind of bosonic particles, as I mentioned in the previous slides. And then it scales as ZQ. That means if the system is heavier, then one can observe these quantities. The signature of these observables can be observed quite prominently. And because of these interactions, now the atomic states, whatever, like we used to say that 1s, 2s, or 2p states like that, we used to say that they have definite parity. But if we introduce these interactions, then the parity will not be a good quantum number in that case. So then all the states will have different mixture of parity states. So each, like 1s state will have a mixture of parity states, and it will be a linear combination of both even and odd parities, and so on. And so the quantity of our interest is the nuclear weak charge, as I mentioned in the previous slide. So then the atomic interaction Hamiltonian that we have to consider. So if you want to consider the total Hamiltonian interaction, PNC interaction Hamiltonian, then we'll have two components, and the nuclear spin independent and nuclear spin dependent. But for nuclear spin independent only, so one can only consider one because they are like these interactions like strengths are very small. These interaction Hamiltonians. So the coupling between both the interactions are very small. So one can neglect that. So that's why one can study these interactions by considering only one at a time. So that is what we do. And so that's why if I want to study only NSI effects, I can neglect safely the NST contribution. And as I said, so the heavier systems will be useful for considering this kind of studies. So that's why cesium, barium, francium, radium, ytterbium, these are the kind of systems are considered in the laboratory. Now the proof of principle for studying this thing or for carrying out measurements is, like, for example, in cesium atoms, so the measurement is carried out between 6s to 7s, and in the francium the planned experiment is between 7s to 8s, and so is 7s to 8s, and so on. So here one can get by, like, if by considering this hyperfine level, so by measuring this PNC interaction amplitudes between two hyperfine levels and taking the average, one can get NSI contributions. So there is some little mathematics involved here. Why we'll get NSI contributions only. And for the other, like if you take the difference, so that will give us a NST contribution, and as well as some contributions from anapole moment. But if we also have like some other transitions in, let us say, in cesium or barium ion, francium, radium ion, something like that, if we get take the transition from NS to ND or D, it could be D3 half or D5 half. So if you take D3 half, so S to D3 half transition, so it will also have contribution from NSI, NST, anapole moment, from all these sources. But if you take S to D5 transition, so one can get contributions only from NST or anapole moment contributions, or mostly anapole moment will contribute here. But anyway, so that is the future study for us. Now here the experiment, why we are like interested in cesium for studying NSI, because the measurement, PNC measurement, is carried out within 0.5% accuracy. Actually, it's 0.35% accuracy by this Carl Wyman's group. And so the basic principle is like the quantity that is measured, that is E1 PNC, that E1 amplitude divided by vector polarizability beta. So here there is a measurement quantity E experiment is mentioned. And what we intend to obtain is QW. So that theoretically we can express this the measured quantity as QW times E1 amplitude divided by QW times 1 by beta. So let us say, so the left-hand side quantity is measured experimentally, and theoretically, if you can calculate U1 by QW, and 1 by beta also can be either measured or obtained theoretically. So, and if all these measurements or calculations are performed within 0.5% accuracy, so by combining them, we can extract QW value. So that is the idea. Then after that, you can compare with the standard model values. And now how to do it? So now let us, if you want to include this nuclear spin in independent interactions in the atomic system, so you have to add then this new interaction contributions to the atomic Hamiltonian, and then E1 PNC amplitude will be calculated theoretically as just the transition, like E1 matrix element between the two states that you are interested to calculate. And if we consider these states, which has a mixture of even and odd parity states, So then there will be computational challenge, because now you have to relax parity as a good quantum number. So then it like the kind of transitions you will see, the amount of transitions that will occur while doing this many-body calculations will be enormous. So then it will be also difficult to determine the accuracy of these E1 PNC calculations. So instead, what we do is, so we treat these atomic wave functions in the portraitative approach. So that means we have this, we express that in terms of zeroth order wave function that takes into account only electromagnetic interactions. Then that first order correction into the wave function due to the weak interaction. And then the GF square order, that means the higher order contributions, one can safely neglect because these effects are much smaller. And now if you substitute this, so the E1 PNC matrix element will just become like, zeroth order and a linear combination of zeroth order and first order, wave function corrections. And here one has to only calculate zeroth order and first order wave function calculations. But the thing is, one has to take into account, so they have to be determined using the same theory. And all these calculations have to be performed, using fast, like principal calculations. But most of the calculations that were reported, so far were not, from the fast principal calculations. They are using some kind of different kind of approach, and that I'm going to, discuss here. So now if you want to obtain these solutions, the first order wave function or zeroth order wave functions based on the first principal calculations, so one has to solve this kind of Schrodinger equation, so for the unperturbed wave functions and as well as for the first order perturbed wave function. And so earlier what people are trying to do, so instead of solving this equation, and you have to remember that these are like linear combination of Slater determinants. So these are not simple wave function, it's a single particle wave function. These are Slater determinants. So what they used to do is, so they used to expand these first order wave functions using this kind of Somerset's approach. And then the expression for E1 PNC was becoming, like given by this expression, which is given bottom of the slide. And for cesium PNC, so the transition was between, between 6s to 7s. So only the p half, orbital, intermediate states will contribute. And based on that, whether n is below the the principal quantum number, like ground state principal quantum number 6, or larger than that, so they used to call this is core contribution. And the rest, when it is n equal to 6 to 9, so then they used to call this main contributions, because that is what they used to, they were able to calculate more rigorously. And the rest, the high-lying states contributions, they used to call tail contributions. So the like when it was divided like that, so the reason for dividing is it was one valence system, so it was very easy to calculate states for 7s, 8, 6s, and 6p half, 7p half, and 8p half, 9p half. So then main contributions was rigorously estimated, but core and tail were not rigorously estimated. And with time progress, so recently, so like many groups started looking at these contributions, and we were one of them. So what we did is, so our idea is to obtain both unperturbed and faster perturbed wave functions using fast, principal approach. So we use a relativistic coupled cluster method, which is known as RCC method, in which wave functions are expressed as some kind of exponential anjaz over here either S acting on some kind of mean field wave function, like which are Dirac wave function. And when I say tilde, so phi tilde involves here parity is not considered as good quantum number, but the same wave function can also be expressed as it were T acting on phi, and where phi n is considered obtained is again mean field wave function, but obtained using only Dirac-Coulomb interaction kind of thing. So that means that conserves parity. But all these parity non-conservation effects will be taken care by the amplitude of this operator T. So what we did is to obtain zeroth order and first order wave functions, we expanded T as T0 and T1, and then the corresponding zeroth order wave function and first order wave function expressed in the coupled cluster theory as given here. And then finally the E1 PNC was expressed like this. And using these expressions and considering only singles and doubles approximations, we had earlier calculated this E1 PNC amplitudes for many systems, at least these three ions. I have shown here. And the first one, actually, it was part of my PhD work in IA. It was done in IA Bangalore, and Professor Budkar was examiner for that work. Then recently we attempted to improve the calculations of CGM, and we wanted to go beyond the single and doubles approximation. So we included triple excitations, and first we calculated this hyperfine structure constants, energies, and so on to test the accuracy of our wave functions. And also we implemented extended our method to include this bright and cute interactions. And then this was the U1 PNC results, and here we have given contributions from core, main, tail, though they are actually included using single theory, but to compare with the previous calculations, so we have separated them. And then earlier the studies, they had estimated core using different theories and main part using different theories, and tail part was using different theory. Main was mainly estimated using Kapur cluster, and core was estimated using RPA or CPDA for a linear combination of that, and tail was mostly from Dirac work. And then what we noticed that, one of the studies, actually this 23 and 22, their PRL papers, and there, like you see that there was a sign difference in the core contribution, and that became a hot debate. So then after that, we did the calculations, and our sign was like matching with the reference 22, and also the core contributions were almost agreeing. So then the authors of 23, they came up with their, like this, gave us some evidence saying that their calculations are correct. So then the question was who is wrong or what is going on, that nobody was able to understand. So anyway, I'll come to that part, but now I want to show some results from our calculations. So now from our calculations, by combining measurement with our calculations, the QW value is given here, and the standard model predicted value is given here. Now by from this comparison, so we found out the new value of sin square theta W value. So that is slightly higher than the standard model predicted value. And then again using this the same like result, so we tried to find out this C1 U coupling coefficient, C1 U decoupling coefficient, and then put some constant over the dark mass of the dark boson, mass of the extra boson, and so on. So the details can be found out in this paper. And then now let me focus on this like the controversy part, the core contributions from various works. So the references are given in the right hand side, 1, 2, 3, 4, and so on. So as you see here, the core contributions like from RPA, Hartree-Fock theory, and Bruckner orbital plus RPA was giving some different sign. Then our CCST calculations were giving different sign. And then the previous study using again using Kapur cluster theory, but then core was taken from lower order many-body calculations. That was also given, it was giving different sign. So then there was some comment in PRD, and we tried to understand this part, that what is happening, why we are getting different sign. Then to understand that, so what we did is we analyzed this expression, because when that matter became a little serious, we went back to the expression that they were using. So like E1 PNC expression, as you remember, so this is given here using the Somerset's approach. Now, if you carefully look at this expression, and this first order wave function earlier is written in terms like, if you in the first expression, HW was considered as the interaction Hamilton, the external interaction. And now mathematically, if you see, if you compare the top equation and the bottom equation, now I have circled something. And if you see the same expression, you can also write down by considering D as the external perturbation. So then you will get a similar expression. But in one case, dipole operator will be the external perturbation. In the other case, the SW will be treated as the external perturbation. But mathematically, both the expressions look to be same. So similarly, one can also write down this expression like it's the same expression, same amplitude, same quantities, but the mathematical the expressions are little different. So what happens is like now, if you want to expand this some first order wave function, and then again you want to define want to call core core, main, and tail contributions as defined here, because these are not single wave function, they are Slater determinants. So the way one can in a paper we have shown that in the references given in the bottom, that the definition of core and valence, they get altered. And that is actually demonstrated diagrammatically in this figure like below, like showing some like MBPT diagrams, how like core diagrams in the MBPT, whatever we call core, and CPDF, that also remains as core. But in the coupled cluster, again, it remains as core in the first diagram. But in the second diagram, it's also again, in like perturbative theory, it is a core contribution diagram. But in RPA, it becomes core again. But in the coupled cluster, it becomes the part of valence interaction. So one of the core contributions now turned out to be valence contributions. It's a basically reorganization of the diagrams. So this definition of core and valence, they do not actually remain same when you treat SW as perturbation or dipole as perturbation, but mathematically the final expression remains to be same. So if you are treating psi0 and psi1 using different theories, so it is like one should not expect that the definition of core and valence should remain same. So that was actually happening. So the final results were almost similar, but the interpretation of core and valence was actually getting interchanged. So that was the debate. So we could resolve that, and that paper is now published in J Journal of Physical Chemistry. So my student who worked on this and found out all the details. And now this is the summary of that work. In the RC's theory, what we did is we had actually solved this psi0 and psi1 using single theory. But in the Dirac also one solves the same thing. That's a Dirac, all everybody's Dirac result matches. But when one uses CPDF method or RPA, so the way this first order wave function are solved is actually little different. And the Juba and Flambau, they had actually used a mixed of the CPDF plus RPA method. So that is why in one case they're for one component like initial perturbed wave function case, so they were considering dipole as first order perturbation, external perturbation, and other term they are considering HW as external perturbation. That's why the definition of the core contribution that was given by us or Derevenko and Flambau, they were actually not consistent. So that is what we found out. But then again, now if you see this theory that one part of this wave function is a mean field wave function. They are not the exact all order mean field wave function, but our coupled cluster theory actually takes care of so both Bra and Ket all are treated in the same way, and they are they include this Coulomb interactions to infinite order. But okay, in the meantime, now if you want to go forward and try to improve the calculation, so these other authors now, like Ginger's group, they are actually Flambau's students or group members. So now they have worked on this electric dipole amplitudes, and they have improved these results by adding some contributions that they had neglected earlier. And also Derevenko and he's one of the postdocs has also worked in the similar thing. So they have included a higher order this correlation effects through coupled cluster theory and improved this one matrix element. So we have to now work towards this also.
Excuse me,
but, yeah,
you have 5 minutes.
Okay, sure. I am going to wind up. Okay. Now the thing is accuracy study. So so already let us say U1 matrix elements one can calculate and compare with the external values the way it is done. But now question is how to find out the accuracy of this weak interaction Hamiltonian matrix elements. So that is basically by studying this hyperfine interaction Hamilton and their matrix elements we are trying to study. It's basically we also make a kind of approximation that we basically calculate their hyperfine structure constants of both states. And then the excitation energy, again, one can calculate and compare with the external result. But here one has to be little careful. In the previous slides, whatever done, for example, what we are doing, when we are calculating first order wave function, the kind of expression we are using is a terminating series expression. But the way the previous the coupled cluster expression, or we are actually getting the hyperfine structure constants or U1 matrix element, it uses a non-terminating series. So this is there is an inconsistency there also that has to be removed, and for that the solution could be one can use bi-orthogonal coupled cluster theory, which we had developed for closed systems, or can think of something else. And then here also another quantity which we did not discuss is the beta value that is also obtained from theory. And earlier, the earlier studies, people had used Somerset's approach, including in our papers. So that also has to be estimated quite precisely. Then only one can get this QW value more precisely. So for that, what we are proposing is, so the hyperfine structure constants, again, we want to start, evaluate using the same expressions, like the way we evaluate U1 matrix elements, and this is called using analytical response theory, and the expression is given here. And beta values also we want to obtain by solving both psi0 and psi1 prime. Here psi1 prime is by just treating a dipole as external perturbation, and that can be obtained by solving this equation. And another thing is one can also calculate this polarizability, dipole polarizabilities, that involves U1 matrix elements as well as excitation energy like PNC. So if you can calculate the polarizabilities and compare with the external values, that directly shows that how accurately one obtains these U1 matrix elements and excitation energies. So this is what we are planning to do in the future. That will be the roadmap for us. And these methods we are now developing. And these are some preliminary results my student has got, but he's still developing. That is not in the final this one. So we are going to finalize soon in 1 or 2 months. So at least some results he has got, and we have compared with the external value. So this is analytical based on the analytical response theory, which is developed for the first time in in this community. And then these are also polarizability values, and we are still trying to improve these results. And that's also now I'd like to summarize that our method, actually RCS method, treats core, main, tail contributions to these PNC calculations on equal footing. And which I did not mention is there is also one contribution called DC double core polarization effects that we are able to include. Our method is able to include that automatically, but in the CPDF method one has to include by hand. And then so we also like the definition of, as I mentioned, the core and valence is not unique. So depending on the kind of expressions one uses, so these definitions will change. So one should compare with the final results of a method than comparing the individual contributions and finding out the sign mismatch or something like that. And so our method also estimates uncertainty to this core, main, and tail, in a consistent manner. But anyway, so we need to work on the basis functions. We need to improve the quality of the basis functions, and we are also working on the this kind of method to study NST interactions and anapole moment contributions. And we are also, our method will work also for calculating beta values from the first principle approach. Now I would like to thank my collaborators. I have on theory, my student Arup Chakravarti, who has developed this linear response theory and done most of the calculations, and Professor BP Das, with whom I have a long collaboration on this kind of work. And recently we had collaborated with Professor Spaceberger from Mainz University on phenomenology of particle physics. And then we are also collaborating with Dr. Aoki-san from Tokyo University and Professor Sakemi-san from Tokyo, and as well as from Riken. So, and then Anders Kashberg from Nice University, France. So they are going to do some of these experiments, and we are going to also they are going to set up this experiment for francium. And so the facility that I'm using is a HPC facility from PRL, Bikram 100. So that's all. So anyway, so again, let me end my talk by thanking Professor Budkar for always supporting me, my work. And though I cannot, there is no record to show here, but I know that personally that how much he helps me for doing my research. Yeah, thank you, Professor Budkar.
Okay, thank you very much, Vijay. Any questions?
Yeah, I have a question, if I may.
Yeah, yes, please. Yes, please.
Yeah, Vijay, thank you so much for everything. I think it's wonderful, actually, that there are several groups that sort of do things independently in terms of the theory of parity violation, and like there is critically assess the work of the other groups that gives confidence in the final result when finally people come to agreement. That's very good. I wanted to ask you, so given the current situation, in theory, what would you estimate to be the realistic accuracy?
See, from now we have a very good control over this, how to take care of electron correlation effects, because we are also going to add more triple excitations and quadruple excitations, at least quantitatively in the future. But what we do not have control over is the QD corrections. Okay, so what happens is like when you say QD corrections, it has two contributions. One is through the wave functions, and another part is through the operators. Okay, so this Ginges and robots, they are working on that, but I am not too much because that we did some QD estimations. But then what happened is I checked that when you estimate QD, then and consider different basis function, there was also the results are not very consistent. And the way QD vacuum polarization effect is like very standard way of estimating that. But the self energy part is a lot, it's not like everybody is not doing it in a like consistent manner. Like Plumbovic does in one approach, then this. This Valmir, forgot his name, from Petersburg. Savayev and these groups are doing in a different way. So recently I had talked to Blondel. Actually, we have a plan. We are trying to collaborate now. So he has another way of doing this. So there is no proper control over the QD part. So that is something is like a open question for us. And then there is recently there was another paper. In fact, you were not there in conference. We had another discussion where this Juba and Flambeau, they were talking about some nuclear polarization contribution. That they say that also quite significant, which we have not looked at, that part. So if they are going to be like problem maker, I don't know about that. But otherwise, if you only ask me about contributions from electron coalition, effect part, so we have very good control over that. So then I can say that we can reach up to 0.2, 0.1% average. But the other contributions which are beyond our expertise, so there I can't make much comment.
And how big are those contributions in the same units? So say percent wise.
It's okay. Electron coalition contributions, you mean the coalition effect? So that we can achieve 0.2%. One, like everybody's project now, even Derevang is projecting that he can get 0.2%, 0.2, 0.3. Because whatever we have, like in our paper, we have claimed that it is 0.3. So in his paper, Derevang has claimed that he has achieved 0.27. But since we are now again further, like improving our codes and working on other things, so it will be further reduced. It may go up to 0.2 or something like that, or 0.15, something like that.
Thank you so much.
Yeah, thank you.
Okay. Any other question, comments? Okay.
Okay, so should I unshare then now?
Yeah, okay. Yes.
Oh, actually, I had a quick question. Is this a new building of PRL?
No, it's we have decorated now. So we have a new director, so who likes to, so Dilip, yeah, so it's just, same building, but it's now whitewashed and looks quite impressive. Coloring, we have just that coloring. Yeah, you visited in 2010 or 9, something like that, when Dilip was there and I was not there that time.
2005, actually.
Oh, 5. Okay. So I was not there. So compared to that, yeah, there is a lot of changes now. Yeah, you should visit anytime. You are welcome.
Thank you so much. Yes.
Yeah. Okay. Thank you.
All right. Thank you, Vijay. Okay.
So actually, I may have to leave because I have to attend this, that meeting going on here.
Okay, fine. Okay,
yeah.
So
okay, thank you, Professor Bodkar. So I may not be able to attend the last part of the session. So maybe I'll talk to you sometime later.
Yes, thank you.
Thank you very much.
Thanks. Okay, so now we have some time, maybe about 5 or 10 minutes for people to make some comments and or if they would like to ask Professor Bodkar any questions, or we have less than 10 minutes. So in about 5 minutes or so, we'll have a lunch break. I mean, lunch for European time, actually. It's probably more like dinner time in Japan. And so I can see Aoki-san. So Dr. Aoki. So would you like to say something, Aoki-san? I mean, about the cesium parity violation experiments, or would you like to ask Professor Budker any questions, any comments?
Okay, thank you very much for Safu-san talk and okay, and thank you, and I okay, so now I will thank the Professor Booker to this. So I think now we are planning to do experiment or cesium parity violation experiment. So, but now for Professor Booker group still do the experiment with the interview afterwards. Yeah. So now I think okay. So, but I think so. It may already have the good result using the several isotopes. Okay. So, but what are the next steps? So, are you still measuring the isotope shift or isotope difference?
Okay. Okay. Yeah. So actually, I I'll answer it in 1 second. But first, I wanted to maybe make a comment about cesium. So this related to Bijaya's talk. So Bijaya mentioned also nuclear spin dependent effect, and the Weinmann experiment remains the only one that actually observed the anapole moment, and it's very, very important to confirm that result, because it's well, some people have different sort of feelings about whether it is in contradiction with non-observation of anapole in thallium, or maybe it just agrees with the current status of nuclear models. But in any case, it's extremely important to measure anapoles again, and maybe at a better accuracy than Carl Weinmann did already, 30 years ago. Anyway, I recently learned that actually there is very good progress from Daniel Elliott at Purdue what they're trying to do is measure anapole using ground state transitions, and so there's a recent preprint on the archive by Daniel Elliott, and I actually invited Daniel to come virtually to our group meeting and explain to us. So that's happening on the 15th. He's gonna visit us virtually and explain this experiment. But I think it's very exciting that there is activity in that direction. So we as you know, we had a terbium experiment at Berkeley, and then we moved it to Mainz, and at Mainz we succeeded in measuring parity violation in a chain of terbium isotopes with about 0.5% accuracy in a single isotope. And we measured it in a chain, and we're able to confirm the standard model prediction that the weak charge is basically neutrons, is determined by the neutrons, and the other result from that was that actually stringent limits on some exotic additional bosons. So usually people interpret parity violation as the limit on the mass of a second boson Z prime in terms of high energy, but there's also another direction. So these extra bosons could be light, but weakly coupled. So we put some limits based on our experiment together with Victor Flambaum's theoretical interpretation of the experiment on these ultra light exotic bosons. Anyway, from there on, we started working on the next steps in our program, which is trying to detect maybe nuclear skins, neutron skins, and also towards the anapole moment measurement in ytterbium. But the recent development is that the postdoc who was working on it, Dionysius Antipas, he actually got a European ERC starting grant to work on this, and he moved to the University of Crete. And so currently we actually don't have any scientists working on ytterbium at mines, and how this is going to develop, we will see. Depends on basically whether I can find a replacement for Dionysius or not. And I don't really know what his plans are, but he has a grant from the European Research Council to do parity violation in ytterbium, take it to the next step. So that's the answer.
Okay, thank you very much.
Any other questions, comments? Okay, if not, then we can take a break. So we'll be back. So what time is it in Germany, Dima?
It's noon.
Okay, so would 1:30 be okay?
Yes, of course. So in an hour and a half then, right?
Yeah, 1:30. Yes. So that will be 6 p.m. India time, and Japan would be 9:30, I think. Yes. So okay, so thank you everyone, and of course thank you Dima and
Thank you so much.
yeah, and for your comments as well. And so I'd like to thank both the speakers, Professor Sadiq Rangwala and Professor Bijay Sahu. And so we will we'll have a break now, and we'll meet again at 6 p.m. India time. So that's 1:30 Europe time, and 9:30 Japan time. Okay. Okay. So see you in about an hour and a half then. Okay.
Thank you so much.
Okay. Thank you. Thanks. Okay. Yeah. Oh, hello, Dima. Yeah.
Hi, Bano.
So I think people will gradually come in. Yes. Yeah.
Oh, I see Sushri is here.
Yeah, I didn't know that she was doing a postdoc with you now. I mean,
Oh, yes.
So Sushri, how long have you been with Professor Budker? How long have you been in his group?
I actually joined last August.
I see. So it's less than a year then.
No, a bit more than a year.
More than a year.
Oh, 22 August. I see. Okay.
Yeah.
I see. Yeah. All right. Okay. So.
Yeah, very nice to see you. Actually, I remember you visited Ashok's lab.
Yes, that was in 2016 August. Yes.
Yeah.
So you were still doing your PhD at that time?
Yeah.
Right.
I finished my PhD in 2019.
90, I see.
Sushri, we don't see you. Yeah.
Just a second.
Yeah.
There you are.
Okay. Yes.
So the next talk is about to start now, right?
Yeah, it should start in 2 minutes. The speaker hasn't joined yet, but I think he will soon.
Okay.
Yeah, maybe I'll talk to you about your experiments some other time, Sushri.
Yeah, sure.
That would be great. That would be great. Yeah.
Okay. Yes. Let's see.
Yeah, so I know many people on the call, but not everybody.
Yeah. Yeah, I had also written to Derek and Victor, but
that's a very, very terrible time for them.
Yeah, I know. So I said that, if you can catch the especially your remarks, your that should be fine. But yeah. Okay. So. Origins should be here. Yeah, so let's see. So yeah, Vijay Sahu said he'll be away because he's being inducted to one of the academies in India.
Oh.
Yeah. So
Amazing. Yeah.
Yeah. So he sort of adjusted his time so that he could
Oh, very nice, very nice. Actually, I was I remember that yeah, he was, I think, one of the two main students that you had at the Indian Institute of Astrophysics in 2005, and is that correct?
Yes.
And he was showing me the new cluster that he was putting together, the computers.
Yeah, exactly. Yeah, exactly. Yes.
Yeah, and of course the other student was KVP Lata.
Yeah, I invited her. I don't know.
Well, it's Sunday, so I mean,
yeah, maybe, yeah. Which is
we maintain correspondence.
Okay.
Yeah.
Yes. Okay. Right.
So there are many very good lifelong relationships that have formed at that time.
Yeah, I know. I mean, yes. I mean, yeah, that is what makes you special. I mean,
No.
Yes. Okay, maybe we can start, and I'm sure others will join soon. So Arijit is here. So then maybe let me then request Arijit to give your talk. I mean, and I'm sure people will start coming in as the talk progresses.
Sure.
Okay.
So good afternoon, Diva, and welcome back after lunch. So I think it's a great way to celebrate your 60th birthday, and I must thank Professor Das for conceiving this idea and bringing together all the people who have been influenced by your inputs in some way or the other. And Professor Das is also very special in my life because he has been my comprehensive examiner when I was doing my PhD at RRI. And then because of him, this discussion with Sadiq followed, and we were able to forge this ongoing collaboration. Victor and Derek had come over for a few weeks. Victor carried on the experiments, and then I think following that, Sadiq visited, and subsequently I visited, and Andrew also had come over. And so there was a whole gamut of activities that spawned, right? And I was quite fortunate that you gave me an opportunity to work with you again in Mainz as a postdoc. And I have no hesitation in admitting that that experiment actually rekindled my interest in precision physics. And the research program that we are trying to develop at IIT Tirupati, which is connected to atomic clocks, is very largely influenced by that experiment because we got a very good exposure to precision measurements when we were setting up the dysprosium experiment again. And because of people like Nathan and Dionysis and Liker Goose, a lot of productive discussions had followed. And, I was completely, overwhelmed by the richness those challenging experiments offered. These are difficult experiments. There's no doubt about that. But at the end of the day, you feel a certain happiness if things work out well. It's a long fight, and it's a long journey. But I think these experiments offer a good amount of spirited challenge in physics, I would say. There's a lot of fun. There's a lot of despair also at some times when things don't work. But then, you keep on going and things finally open up. So this talk that I'm going to give right now is connected to our ongoing activities connected to the development of a portable trapped-ion atomic clock. And I will try to dwell upon the physics motivations as well as the applications, because the project is funded by largely funded by the Technology Innovation Hub at IIT Tirupati. And one of the mandates for that hub is that they promote translational research. So while the project is connected to the portable atomic clock, because we have to abide by certain guidelines of the funding agency, we of course are also well motivated by the physics implications such devices offered. And I hope that I can share some insight and maybe it'll be interesting to the audience. So with that, let me share my screen, and I'll try to start my presentation very quickly. So if you can see my screen, please let me know. Right, great. So so the title of my talk is Towards a Trapped Ion Portable Atomic Clock and the Prospects for Fundamental and Applied Applications. So I'm very fortunate once again to give this talk in honor of Professor Budgar's 60th birthday, and I thank Professor Das and Tanmay and all other colleagues at TCG Crest for organizing this nice symposium. So with that, let me proceed. So the plan of the talk is that I will try to briefly dwell upon the motivation. And when I talk about the motivation, I will divide it into two segments. I will dwell upon the physics as well as the technical motivations of why we want to do this or pursue this activity. I'll try to share some brief background on the physics of atomic clocks, the current methodology that we are following. So this project is in close collaboration with a lot of former colleagues and friends, and principal among them are Professor Sadiq Rangwala at RRI, Professor Shubhadeep De at IUCA Pune, Professor Amar Bhuta at the University of Toronto, and Dr. I forget the name. He's at NPL, New Delhi, and Professor Vijaya Sahu, who is also given a talk today earlier on in CP violation. I think I should also mention all the students and colleagues who have really helped us, put forward this program at IIT Tirupati. And then I will finally end with some future directions, challenges, and opportunities. So once again, as I said, this project, the science motivations are quite well connected to what we have learned so far from my stay at Mainz. So the motivation for developing an atomic clock, one of the fundamental motivations is to look at precision spectroscopy and how precision spectroscopy can share some insights into new physics. So as we know, the known universe in our own knowledge is comprising of matter which is less than 5%, right? So if you look at all the particles in the standard model and all the matter element that we see around us, it's less than 5% of all the total matter content of the universe, right? And so you have two large segments which are completely unknown. One is a dark matter segment, which is around 24%, and then there's a dark energy segment, which is about 71.4%, right? And there's a nice review article published in 2018 by Dima and other colleagues, where they talk about the implications of new physics and the searches for new physics in different contexts. Okay, so if anybody's interested, it's a very nice article, and he or she should definitely go through that. So when we talk about dark matter, for instance, right, we see that there's an overwhelming astrophysical evidence for dark matter, right? It's about 5 times more dark matter than ordinary matter. And one very strong likely question that comes up often in the discussion is that what is dark matter, and how does it interact with ordinary matter non-gravitationally, right? So we have this dark sector that you can see on the screen here, and we want to figure out, okay, or we want to find out how these dark sector particles couple to our known standard model sector particles, what kind of interactions are manifesting, what are the energy scales, what are the length scales, what are the mass scales. So these are open questions that people are trying to figure out, right? And there are various approaches. I'm not saying that the atomic clock is the best way or the only way that you can actually probe these interactions. Nothing of that sort. It's just one of the possible ways. And interestingly, it's quite well motivated, right? So if you look at our own Milky Way, right, you can see there's this dark matter halo around it, right? And there have been previous astrophysical observations. For instance, if you look at the motion of gases in galaxies, okay, you would see that they maintain a fixed velocity, so to say, as you move away from the center of the galaxy, right? This is completely counterintuitive with respect to the Keplerian or Newtonian laws of motion, right? And so this suggests that because you are maintaining the speed even for distances which are quite far away from the center of the galaxy, it is quite likely that there is some additional invisible force or energy that is helping this speed to sustain, right? Apart from this, so this was way back in, I think, 1934 by Woot and Zwicky. And then, of course, there's this CMB background radiation, which again hints at the existence of dark matter, right? So as you can see, the existence of dark matter is well established through different astrophysical observations. And so there are now these searches for elusive dark matter particles, right? So there are many theories which go beyond the standard model, predicting new particles or interaction, new type of fields, scalar field, vector fields, and so on and so forth. And essentially, it's not like a single theory that is working out for every possible interaction. So depending on what type of problem you are attempting to solve, you try to motivate the existence of a new particle or field. And so you have these fundamental physics problems like the matter-antimatter asymmetry, or let's say the hierarchy problem, or let's say the strong CP problem. And these problems have been there, and the hope is that there might be some well-motivated experiments, which are currently ongoing, that may shed some light into some of these problems, right? And typically, what you would expect is that the violations of fundamental symmetries, or let's say the variation of fundamental constants, which was, I think, one of the major experimental programs that DIMA had going in Berkeley. For instance, this alpha variation experiment, these are well motivated with the search of new particles or fields that go beyond the norm of the standard model. So the thing is that, while we are talking about these new fields, not all of them may connect to dark matter. They may not, right? And so there is this competition between different theoretical and experimental groups, where one group may be motivated for looking for particles which are in the extreme high energy range, or some of them may be motivated for low energy range, right? And so there are extreme, I would say, approaches towards this problem. And so far, there are at least to my knowledge, we don't have a concrete answer to these problems, right? So this existence of dark matter is confirmed by numerous astrophysical observations, and is a new physics to look for, right? So we know how much dark matter there has to be in our galaxy, but then the question is, how can we probe it on through experiments on Earth, right? So most of the beyond standard model searches are related to dark matter and dark sector searches. So coming to atomic clocks, right? So what essentially is an atomic clock? Well, you have, let's say, these well-defined energy levels in atoms, and one can choose to measure the frequency difference between these energy levels to an extremely high precision, and then use that as a frequency standard or a timing standard, right? And the motivation is that when dark matter is passing through this known matter, okay, for instance, this known atom or molecule or whatever somebody is working with, that dark matter element may be able to perturb these energy levels ever so slightly. And if somebody is able to measure that tiny shift with an extreme precision, then there is a possibility that one may be able to detect the hint or existence for new particles or fields beyond the standard model, right? So the idea is that this dark matter is going to shift this energy level very small amount, and it's only with the help of very high resolution spectroscopy that one is able to measure that tiny change, and hopefully through well-motivated theoretical models connect it to the existence of particles beyond the standard model. So researchers so far have proposed numerous models, numerous particles that explain astrophysical observations, and they also conform to results of previous experiments. And the one example that I would like to highlight here, which is connected to the recent works done at MIT by Professor Bledan Vuleti's group, and at the University of Aarhus, Denmark, by Professor Michael Drussen's group, is they were looking for some kind of a dark matter boson that is predicted to interact with ordinary matter. And the idea was that these dark bosons would be virtually exchanged between an atom's electron and neutron and induce extremely tiny forces, which would then change the atom's transition frequencies, right? So it goes back to the idea that I explained in the previous slide. And both these teams were actually trying to detect this small, extremely tiny changes in this atomic energy levels through high resolution spectroscopy. So the two teams, they used two different elements. The Aarhus team used calcium and the MIT team used ytterbium, and they measured a couple of transition frequencies across multiple isotopes, and then they constructed a King plot, and they tried to look for a nonlinearity in the King plot, right? And what they realized is that the Aarhus experiment did not show any deviation, but the MIT experiment predicted some deviation, some amount of deviation. Interestingly, as I mentioned, that these dark matter searches are not related specifically to optical clocks. Traditionally we have been witnessing dark matter searches through other experiments. For instance, the Xenon collaboration in the same year, they also reported seeing some additional light that matched those expectations from a dark matter called dark bosons. But then subsequent data analysis in 2022 disproved that existence. So technically speaking, the MIT experiment is the only experiment where they potentially see some deviation with respect to the King plot, and which could possibly hint at particles beyond the standard model. So here I am just sharing some results from the Vuleti's group, where you can see the different couplings being plotted against the boson mass, and how they are looking at the different nonlinearities, okay, that may crop up based on the theoretical model they are pursuing. Similar kind of measurements done on calcium through, by the Lucent group. And this is again a plot which is showing us the projected coupling strength, okay, of the new particle to the electrons and neutrons in this particular element, right? And these measurements have been done on the calcium ion, and they have been done at a precision of about 20 hertz, right? So this is quite a promising sign, and one can hope that if these measurements are improved to higher resolution. So if you, for instance, look at this line here at 10 millihertz scale, there is a lot of impact on the understanding of this dark matter field. Whether we are able to come to that resolution or not is still an open challenge, right? So what we see so far is that the Vuletic group is the only group that has reported this departure from predictions, and they have found a deviation statistical significance of 3 sigma, right? So they're careful in their claims. They're saying that yes, it's consistent with the leading correction to the standard model prediction, but it could also indicate the existence of dark bosons, right? And so what I wanted to show you through these experiments is that the importance of atomic clocks. Yes, you do have a lot of applications in the real world, but there are very good physics motivations why it's important to develop such kind of programs in the country. So it connects to fundamental physics in a very deep manner, and we hope that the program that we are trying to develop at IIT Tirupati would be able to look into some of these aspects in the long to medium term. So since I mentioned that I'm going to talk also about some real life applications of atomic clocks, one of the most major applications is with respect to PNT, where we talk about position, navigation, and timing, right? So when we talk about positioning, it's essentially to determine one's location and orientation on a geodetic system. Basically, we're talking about the Earth. And when we talk about navigation, it's about moving from one point of the Earth to the another. So you have latitude and longitude coordinates. And so you would like to check your, let's say, what's the direction or orientation and speed needed to reach your destination from one point to another, right? And connected with both positioning and navigation is timing, because typically how this works is usually you have this whole constellation of satellites moving around the Earth, and each of these satellites has an onboard atomic clock. And so when you want to pinpoint your position on the surface of the Earth, you turn on your GPS receiver on your cell phone, and immediately that beams a signal, and that signal is then triangulated by 3 or 4 satellites where the pinpoint location precisely on the surface of the Earth using some latitude and longitude coordinates. So when you use PNT in combination with some map data or some other information, what you get is this GPS system, right? So for instance, in India right now, we are trying to develop our own GPS equivalent system, which is called the NAVIC. And for that, you would need your own indigenous atomic clocks, right? So here, as you can see on the screen, this is the existing PNT architecture, where you see the GPS satellites are beaming signals, and they are supporting a whole host of applications, right? For instance, you also see NAVIC here, right? And they are connecting multiple domains. They are connecting networks, they are connecting navigation, both in terms of air, water, and surface. Then you're talking about strategic communication. You're talking about financial markets, and so on and so forth, right? So the PNT domain is an overwhelming domain that connects all of us in a daily basis. So, of course, there are issues that the PNT domain faces, and some of them connect to jamming and spoofing. Some of them connect to out-of-date maps, or your signal gets lost because of different high-rise buildings. Okay, so it's very important that you come up with some solution that can comprehensively address some of these major problems that the PNT domain is facing. And one of the ways to overcome the problems that the sector is facing is to come up with a resilient PNT system where you combine different kinds of sensors, and you fuse the data with from these different sensors, and then you build up a resilience to the existing GPS or NAVIC system, such that even if because of some reason your access to GPS or NAVIC signal is blocked out, you would still be able to perform your daily work, okay, as usual, because you now have access to a timing source that works optimally, which is pre-synchronized to your GPS or NAVIC network, right? So for that, you need to have a system that not only has optical clocks, it also has inertial sensors like gravimeters. And I know in TCG Kolkata, Dr. Aishik's team is actually trying to develop one gravimeter experiment for these kind of applications, right? So in terms of real world applications, most of them rely on this 1 microsecond synchronization. For instance, you're talking about communication networks or navigation networks, you're talking about power grids, financial time stamping. So these 1 microsecond synchronization is usually achieved via connecting to the GPS signal. Now, the issue is that the GPS signal can be intermittent, it can be noisy, it can be jammed, right? And so one needs a reliable holdover clock or a timing reference. So one can come up with different solutions. So one can say, okay, why not use a oven controlled crystal oscillator, right? The issue with that is it can only hold 1 microsecond synchronization for about a few hours, right? Then there's this other very attractive option, which is the chip scale atomic clock, which can hold 1 microsecond synchronization with respect to your GPS signal for about 8 to 10 hours, right? But then if you're blocked out of your GPS signal or NAVIC signal for more than 10-12 hours, then a good option to use is an optical atomic clock, where you can potentially have a synchronization over 1 microsecond time scale for more than 2 months. So what you need is you need a field level device which can be used outside your conventional lab environment, and you also need a device which has low size, weight, and power. So when we talk about a clock, we're talking about a system which has a periodic behavior. So there should be something which is repeating or cycling at a regular frequency, right? And then one can count the cycles to produce some kind of a time interval, and then agree on the origin of time to generate a time scale. So this is the basic principle, right? And when we talk about an atomic clock, the advantage is that when you use a particular atom from a given element or given isotope, any atom from that is the same, right? And they will oscillate exactly at the same frequency, right? So you kind of have a perfect natural oscillator, right? So the idea is that you could take a sample of atoms, let's say, through a cold cloud, or maybe you can trap a cold ion, and you can use a laser to excite the atom or the ion from one level to another, and then you can then measure this laser frequency extremely precisely with the help of a frequency comb, right? And one can then count the number of signals of the cycle, okay? And create some kind of a timing reference, right? So here you see the block diagram of an optical clock. You have an atomic reference, okay? You have the oscillator, which is the laser, and then the counter is your frequency comb. And the frequency comb is a fantastic device that converts signal from the optical domain down to the megahertz range, right? So it gives you a usable user input at a 10 megahertz reference rate, or a 10 pps signal rate, which is conventionally used for different applications. So the reason that one wants to go from the conventional microwave based optical clocks to an optical based atomic clock is that if you look at the clock instability, you would see this particular factor hiding here, and this is basically connected to the inverse of the quality factor, right? And so this tells us that if I actually have a clock that operates at an optical frequency, my quality factor would improve by many orders of magnitude, and this would actually improve the clock instability. So there is a very good reason why one would want to shift from a microwave to an optical device, right? So if you want to look at the improvement of how to go to a lower instability, you would have to work around these two factors and choose an atom or ion appropriately to take the natural advantage that comes with that particular transition frequency. So when we are talking about ion-based atomic clocks, typically we are talking about forbidden transitions in single trapped ions. So for instance, as I mentioned, calcium, for instance, you could have a calcium transition from S to D, which is connecting to this metastable D state, right? And typically that's a dipole forbidden transition, but then it's weakly connected, and one can use this particular transition to build some kind of a clock transition, right? And the advantage of using the ion-based atomic clock is that if you look at a single trapped ion in between the electrodes that form the trap, there are some nice advantages to that system. So one option, one advantage is that you don't see any first order Doppler shift, okay? Another very big advantage is that you have a very minuscule second order Doppler shift. The field perturbations are also minimized at the trap center, and because it's a single ion, the background collision rate is quite low, compared to, for instance, if you had an atomic cloud here, right? So the reason we want to work with calcium is that it has a relatively simple energy level structure, right? So there's no nuclear spin. The nuclear spin is 0, so there's no hyperfine splitting of the energy levels. So it's a big advantage, right? Because there's a number of lasers required to cool the ion that reduces dramatically. So if you compare the energy level structure of calcium versus ytterbium has a much more complex energy level structure given the existence of hyperfine energy levels, right? Also, a big technical advantage is that the lasers for cooling and repumping calcium ions are at wavelengths which are commercially available. So you can get cheap laser diodes and cheap laser diode systems. The advantage of using calcium is that it has multiple isotopes, and you already saw that I highlighted these results from the Aarhus group, where it was looking at possible, implications of new physics models through precision spectroscopy. And they could do that because they could measure multiple transitions across a whole bunch of isotopes in calcium. So it has the potential to serve as an accurate clock. And one big advantage is that it can operate at a unique magic radio frequency trap. And that would actually cancel the micromotion-induced scalar Stark shift and the second-order Doppler shift, right? So that's another big advantage, that if one would operate the ion trap at this magic RF frequency, you would be able to cancel the second-order Doppler shift with the micromotion-induced scalar Stark shift, right? And here I give you the different isotopes of calcium and the natural abundance, as you can see here in brackets, and then all the different transition frequencies of the various levels with respect to the first one, right? So, as I mentioned, this current project is a collaboration between Professor Rangwala's group at RRI and Professor Shubhadeep Dey's group at Ayuka Pune. Ayuka. The system that we have developed is a very compact system, and we are currently testing this system at RRI. So we have manufactured one prototype, and it's currently under testing at Professor Rangwala's group. Not only the trap, but we also want to develop a whole bunch of compact laser systems, control electronics, because we want to make this entire system portable, so that it could be carried out the usual lab environment, and you could make it field operatable. So these are some of the features that we want to aim for. So with respect to the trap that we have designed, I would like to highlight some of the parameters. For instance, the applied RF frequency is very close to the magic frequency. The RF voltage is around 300 volts. We expect a radial secular frequency of about 8 megahertz and axial secular frequency of about 1 megahertz. So this two frequencies are important in the context that one would want to do some kind of a ground state cooling of the ion, and so this kind of well-separated values in secular and axial frequencies, radial and axial secular frequencies, gives us the opportunity to do this resolved sideband cooling on the trapped ion, and ensuring that it occupies the lowest motional state on the ion trap ladder. So here I can show you some of the simulated trajectories of a trapped ion, and here we are looking at the power spectral density of the different motional frequencies. So this band here is coming from the RF that we are putting in, and these are, you can see the secular frequencies coming from the ion, right? So quite well separated, very clean spectrum. So we are hoping that the ion would be able to be cooled down to its motional ground state in a very comprehensive manner. So
excuse me, Arijit, sorry, you have about 5 minutes.
Sure.
Okay. Sorry to.
It should be fine. Yes.
Okay.
So along with the development that is going on with respect to the ion trap and the associated electronics to control the ion trap, we are also developing a optical cavity system, because in order to excite the ion across this extremely narrow frequency value, which is connecting this the ground S half to the metastable D3/2 or D5/2, one would need a very, very stable laser, and the only way one can achieve a stable laser at that level with a line width of, let's say, less than 1 hertz is to stabilize the laser on some kind of an optical cavity, right? And we are trying to develop our own design. We are doing some simulations on the computer based on finite element models to look at the stability of the laser spacer, the cavity spacer for different kinds of fluctuations It can be mechanical stress, it can be thermal stress, it can be some kind of acoustic stress because of wind velocity. So we are trying to model some of these elements in this particular computer-aided simulations, and trying to optimize the design. So we are looking at, as I mentioned, we are looking at trying to improve the stability of the cavity. This is very critical because we are trying to use this platform outside the lab environment, and we have to make sure that the cavity is stable to a very high degree, such that the laser which then gets stabilized on the cavity is able to drive this particular transition connecting the S half to the D 3/2 or 5/2 in a very coherent manner. So here I show you some of the preliminary diagrams of the ion trap that we are planning to mount. So this is the vacuum system that we have evolved. We are planning to integrate this ion trap in this kind of vacuum system. You can see these large windows for optical access for the beams to come. Also, it allows you a good degree of freedom to collect the ionic fluorescence because of this huge opening. So we are trying to optimize the design, trying to come up with a design of an imaging system which will probably have one of the elements inside the vacuum chamber, and see how to integrate that with the setup in a compact manner. So one of the students, Vikrant, he is working on this particular project, okay? And Rishabh, who is another student, he is working on this cavity design project. So the hope is that we come up with a system which is on wheels, which is compact. So it will have the physics package system, it will have the laser system, computer control, you have the cavity, the frequency comb, and finally the conversion unit, which will convert the optical to the usable 10 or 100 megahertz or 1 PPS, whatever the usable output signal is required for practical application. So this is our final goal so far as the applications are concerned. So the current status is that we have 2 students, Vikrant and Rishabh, working on this project. The UHV system is under development by Vikrant. The high finesse cavity system is under development by Rishabh. And as I mentioned, the prototype trap is ready. It's under testing with Professor Sadik's group at RRI. And we have a second trap getting ready very soon, which will probably be tested by Professor Shubhadeep group at Ayuka. Vikrant recently got awarded a PMRF fellowship, and he also got awarded this MITEX fellowship when we visited Professor Amar Bhuta's group at the University of Toronto. So we have quite an active collaboration with numerous national and international research groups in this area. And we are also talking to a bunch of industry startups with the motivation of fostering indigenous development of technical subsystems relevant for the project. So this is my acknowledgement slide where some of the key collaborators are listed. We are fortunate to have funding from the KMOST initiative, from the Technology Innovation Hub at IIT Tirupati. We also have been supported by Chanakya Postdoctoral Fellowship from the iHub Quantum Technology Foundation, IISER Pune. And we would like to thank all of our collaborators for this particular project. So with that, I would like to conclude my talk here. Thank you for the patience, thank you for your time, and thank you for this wonderful opportunity to present our work here.
Okay, thank you very much, Arijit. And any questions? We have time for some questions or comments.
Yeah, sure. I would be happy to take some questions or comments. Yes.
So, may I ask some things?
Yes, please.
Yeah. Thanks so much, Arijit. That's very interesting. I think there is some more recent work on this isotope shift business precision isotope shift measurements, some published and some not.
Right.
Yeah. So first of all, Vladan measures isotope shifts in the terbium ion.
Right.
Yeah, and we've done a measurement in the neutral, and then we were able to do a King plot where you have ion transitions versus neutral
atom transitions.
Neutral transitions, and that was pretty interesting because that actually further gave some further input on this stuff. But then there is a group in Japan, I forgot where, that does cold atoms, and they have done we did an atomic beam measurement, so with 300 hertz precision or something, and they were able to do better with cold atoms rather than.
So this is in Japan, in which university?
I forgot. But if you look at something like precision isotope shift ytterbium and in Google, you'll find them. Or if you can't find them, ask me. I'll find it for you.
Sure.
And then there is some very interesting recent work in the group of Tanya Minstoiber and also Pete Schmidt at PTB. They're doing fantastic work. And in the meantime, there's something that I wanted to mention to you that may be of interest to you. So most people at the moment, they only work with spinless isotopes because they say, well, if you go to the isotopes with hyperfine structure, there's so much more theory that needs to be done. But we had some very interesting discussions with theorists, and I think that there will be an effort to get the theory to the level where it's actually possible to include the odd isotopes, so the non-zero nuclear spin isotopes. So my request to you, when you get to the measurement, don't neglect those. Also measure those.
Sure. Definitely. Yes. The even isotopes part actually has been done. Let me flash that slide again. As you can see here, all the even isotopes have been done at a quite high level, about 20 hertz precision. By the Aarhus group. I tried looking up for any extensions of their work, which may have they have put up in the archive, but I did not find anything as a follow-up measurement from their group. But for the Vuletish group, they published another PRL last year, 2022, which I think I highlighted in one of these slides, probably here.
Yes, I think that was about the same time we published our.
I see. Okay. So that's very interesting that you combine this ytterbium ion and the neutral atom, and you see something interesting in that also.
It's fine. It doesn't have to be the same ionization stage. And the other thing, maybe another quick comment if we have time, that the story of this isotope shift was a little dramatic, and I guess now it's all in the past, but the first ideas were formulated by Gilad Perez and his students, and they were very strongly criticized by the community. Yes, they had some imperfections in their original proposal, but their core idea was, of course, brilliant. And I remember there was this meeting on what is called the precision physics with simple atoms, and there were like very kind of animated discussions of this. Anyway, so at that meeting, actually, I met Gilad and somehow ended up joining that effort. And together we were able to flip the opinion of the community.
Absolutely.
And then actually some of the Victor Flambaum was very critical, but we managed to convince him. And so on this 2018 paper that it proposes this Victor, and then we brought also Julian Berengood on board.
Yes.
Yeah.
Julian has been a key player now, right? I mean,
Actually, I was the first author on that paper, but then I proposed to bring Julian in, and so I became the second. Okay, just a little anecdote. Yes.
Sure. Nice. So yeah, if there is any other
So
question,
can I come in?
Yeah. Please go ahead.
Hi. Can you see me? No, you cannot see me. Hi.
Now we can see you, Sadik. Yes, please.
So I just wanted to say one thing.
Right.
It is very possible that this weekend we have seen the fluorescence from the ions in the ion trap.
Wonderful.
Okay.
Fantastic.
So I mean, I have to go and check what happened. On Monday we will know.
Okay, wonderful.
For sure.
Wonderful.
Okay, but so it may be that we are in business.
What an occasion to report this news. I'm so glad. This is fantastic news.
Well, if it is misreported, then I take no responsibility.
Oh no, I'm sure the students have verified it. I'm happy. Okay, great. Good. So thank you for the update. And so looks like we are in business with the ion trap.
Yes, it looks like we are in business with the ion trap.
Okay, great. Okay. So any other comments, anything that we would like to discuss on the presentation I made from the audience?
Okay, so maybe we'll move on, but that's very good news from Sadik, and that about the ion trap. So we can now move on to the next talk. That's by Dilip and Brajesh. So they will together talk about parity violation in ytterbium, neutral ytterbium. Okay.
Yeah, so am I audible?
Yes, please go.
Yes. Hey.
Hi, Dima.
Hi, Dilip. So good to see you.
It's
You haven't really
to see you.
You haven't really changed very much.
That we will find out. Okay, so I'll just share my screen. Yeah, so what I'll do is I'll just give a few slides, and then most of the talk will be given by Brajesh. I'll talk something which is not entirely academic, but that may be of very much interest to Dima. So regarding the topic, so thanks to Professor B.K. Mani in IIT Delhi and his team. So the sign problem concerning the NSD-PNC of YB has been resolved, and he will be reporting some preliminary results. But this may be of more interest to Dima. Are you able to see the screen? Yeah. So I'm going to answer a question that was posed to me by Dima on 17th of August of this year. So you see the photo here. So now you see how much who has changed and who has not changed. And this is Dima here, almost 18 years and 1 week back. He was in India, in Navsari. So Dima had asked me this question. Would you happen to remember the name of, okay, sorry, just a minute. Name and title of the important Zoroastrian priest who gave us audience in Navsari, sea below. Right, Dima, this was your question? Okay, so this is going to be non-academic. Academic part, Brajesh will deliver the talk. Okay. So the person in the middle between Dima and me is Vada Dasturji Meherji Dastur Kekobat Meherji Rana, the high priest of Parsis in Navsari. The 16th Dastur Meherji Rana, he was one of the 6 Parsi Vada Dastur high priest in the world. So Dima, this is your answer. This is the answer to your question. And
thank you so much. And I would like to have a copy of your slides, please, Dilip.
Yes. Okay, so this was the photograph that was taken when Dima visited Ahmedabad in 2005, and we had a great trip to Navsari in Gujarat. And as we progressed, I have very few slides, but you will come to some interesting aspects of the visit. And this is a very Parsi high priest is highly regarded, and he was born in 1935 to a family of the 15th Dasturji Meherji Rana. So he was trained in Mumbai in one of these madrasa, and he became 16th Dastur Meherji Rana on 26th July 1960 at a very young age. That's at 24 years. And he left this world on 23rd January 2010. So he is no more with us in this world. He sort of passed away quite young, as of the way how things are today with the medical care and so on. So what you see at the background, Dima, you see here this portrait. This is the portrait of the first Meherji Rana. So this portrait. So that is how it was started. So he was the first Meherji Rana, and he was given this title by the Parsi community because he performed so well during an interaction with the Emperor Akbar, that is the Mughal ruler Akbar, in 1578. And the descendants of the Meherji Rana, they were named as Dastur Meherji Rana. So he was the 16th whom we met. And
sorry, Philip, can you repeat? Emperor of what?
Akbar.
Akbar. Thank you. I didn't hear.
Yeah. So Akbar was sort of trying to learn many aspects of different religions. For the Zoroastrian religion or the Parsi religion, Meherji Rana, the first Dastur Meherji Rana, was the person from whom Akbar learned about Zoroastrianism. Okay. So then afterwards, so when Dima wrote up, so lost in translation. So how Dima became representative of Zeus in California. So Dima wrote prior to India visit about his intention to know more about Zoroastrianism. So what I did was I contacted one of my colleagues from Kerala, a Keralite colleague who works in PRL. He in turn contacted a Sindhi friend from Surat, who in turn contacted a Parsi from Navsari. And in the process, my words, a Jewish collaborator from Berkeley wished to know more about Zoroastrianism, got morphed into a Jewish representative from Berkeley, Dima. So that's how it happened. So now so Dima, you have seen southern, western, eastern parts of India. So next agenda could be that you come to Northeast India, where I am now, and explore some of the unique features of this region. So Dima, so we have had a very long and a cherished friendship in terms of academic, non-academics. Perhaps these few slides would have shown that how far it has gone. Now we can stretch it further, come to the northeast part of India. Let's explore some unique features of this world, of this part of India. And let's continue our communications. So that's where I stop. Now I hand over the presentation to Brajesh, who is, I'm more of an assistant to Brajesh these days. He does most of the theory work, these intricate structure and properties calculations. So for the academic part or the scientific part, I hand over to Brazis. So there that is. Dima.
Any comments on what Dilip presented, or shall I proceed on?
You can
So,
proceed.
this is Sadik. I just want to say that like Dima had assigned you with an identity, with establishment of identity. He assigned me too with an establishment of some identity in some photo he had from such visit. And when you flashed this slides, I remembered that I had actually found out who the people were, and I have sent it to Dima. So
Okay.
thanks. You just reminded me.
I never got it, Sadiq. I never got it.
It's on your WhatsApp.
I will check. When did you do this?
Just now.
Recently?
Just now.
Okay. Great. I just, if I have one comment, Sadiq, next time I'm in India, I'm coming to visit you for sure.
Oh, absolutely. Always welcome, Dima.
Yeah, did I say Sadiq? Sadiq too, but also Dilip.
Hey, now you have spoken, Dima.
Of course.
You're not allowed to walk it back.
At Bangalore, I'm a frequent visitor, but in the north, I haven't been. So both. So I'm coming to both.
Great.
All right, so shall I start?
Yes.
Yeah, okay. Okay, so I would certainly like to thank Professor BP Das for giving me this opportunity to speak on this, I speak in this wonderful symposium, because I feel nothing can be better than this for me to speak on YBPNC in front of Professor Budkar. So that I am very proud about that. And yeah, so I will start by congratulating Professor Budkar on completing this very important milestone of the life of these 60 years. And from my group, from myself and from my group from IIT Delhi, I wish him all the best for the future and a very happy 60th birthday. As far as my interaction with him is concerned, I see an important trend here. So I first met him in 2005, November. That was his first visit, what Dilip mentioned about. And my recent visit, recently I met him in July this year at ICTS. So the first is his first visit, I met him, and the recent visit I met him. I was not fortunate enough to make it for this in between two visits because I was away from India for postdoc. Okay, so with this, I again congratulate him for completing this 60 years of life, and all the very best for the time to come. So in terms of this physics, this is my plan of the talk. So I'm going to, somehow I cannot see. Yeah, so let me switch on the pointer if I can. Okay. Major pointer, yeah. So yeah, I'll start with the basic introduction of the PNC in YB because that is what is of interest to Professor Budkar. And then what are the theoretical observables we look forward to calculate so that we can compare with the experiments. And then some preliminary results on YB PNC, which we have carried out at IIT Delhi. And we are still in the process of refinement, so that I will share with the people. So as we know that PNC, the first indication that parity could be could violate, that was in notice in this famous theta tau puzzle, where these two particles were found to be exactly same, except the difference in their mode of decay. So the theta was found to be disintegrating in 2 pions, and the other tau was found to be disintegrating in 3 pions. And later, Li and Yang, they found that it was because of the parity violation. Now, if you talk about the PNC in atoms, so PNC in atoms in particular, so that was first pointed out by Zeldovich in 1959, and what he showed that the PNC strength or the PNC can violate in hydrogen atom. However, since hydrogen atom is a very lighter atom, the signal was so weak that it could not, it was not measured, or it could not be measured in the experiment. Now, the main breakthrough came in 1974 when Marion Bouchiat and Claudie Bouchiat, they showed that this PNC in atoms or ions scales at the cube of the proton number, and hence it was more likely to be found in the heavier systems. And following their suggestions, so many PNC experiments were conducted, and so far we have measured PNC, or we have found PNC effect in cesium, thallium, bismuth, and lead. Among all these, the most precise measurement, as Vijay was mentioning, and also Professor Bhutkar himself mentioned during the discussion, that it was by Carl Wyman group in 1997 in the case of cesium. And the precision of the measurement was 0.35%. And in fact, this is cesium is the only system, in fact, where the theoretical calculations are very, very precise as well. I think the most accurate calculation is about 5% or so. So the next atom, which is of our interest as well, that was the YB, in which PNC was measured. And that was, in fact, by Professor Bhutkar groups himself. And the first measurement was in 2009. And so far, I think there are a series of measurements in his group that I'll talk about. And over the time, the precision in the measurements have gone up very, very high. So the system of our interest is cesium and YB. That is what we are looking at IIT Delhi. In fact, to be more importantly, we are looking into the NSD component of the PNC, which is, we feel that less explored, and that has a lot of importance in terms of enapole moment and understanding the nuclear structure. However, for this talk, I will be just talking about the YB. Cesium, we have done NSD PNC calculation, which we are in the process of drafting. But in this presentation, I will be focusing about YB, because which is the atom which interests most to the Professor Bhutkar. So yeah, why YB? So the YB, in the case of YB, so this diagram I have taken from one of the papers from the Professor Bhutkar. So all these experiments I have listed here, they are from his group only. And the PNC transition in YB is between 6s2, 1s0 to 5d6s, 3d1. So this is the forbidden transition, but it violates the parity. Now the YB is important because in 1995, David DeMille, he pointed out that the PNC effect in the YB is almost 100 times larger than cesium, so which makes it easier to detect and probe. And in addition, YB has a series of naturally occurring isotopes. So if you do the measurement across a series of isotopes, then it can help us in understanding the nuclear structure. And more importantly, the PNC signal in the YB has a dominant contribution from the nuclear spin-dependent part. So that can help us in understanding or predicting the nuclear enapole moment. So these are some motivations which make YB important candidate for PNC. I already mentioned that the first experiment was done in 2009 by Professor Bhutkar group, and the uncertainty in that was, I think, about 14% or so. And since then, series of experiments have been done there. I have mentioned here some of them. And this recent experiment in 2009, that had the uncertainty of about 5%, 0.5%. If you look into the calculations, so the first calculation about NSD PNC in YB was done by Professor BP Das, followed by Dilip and Professor BP Das. And then in 2000, Parshev and his collaborators, they did. Recent calculation, or the most recent calculation for YB PNC, especially the NSD PNC, was done by Vladimir Juba and Victor Flembaum. That was in 2011. And if you look carefully here, the best accuracy achieved is 13%. So if you compare experiment and theory, we have theory people have long way to go. And we need precision or the more accurate calculations if you want to have a meaningful comparison between experiment, atomic experiment, and theory. All right, so just for completeness, so sources of PNC. So there are two important sources of PNC in atoms. One is the conventional neutral weak current interaction between electrons and nucleus, which is mediated by the Z0 boson. And the second one is the electromagnetic interaction between electrons and the nucleus. So the electromagnetic interaction as such does not violate the parity, but the n-pole moment violates the parity. It is an odd parity moment. So the interaction between electrons and the n-pole moment of the nucleus is a parity violating interaction. So these are the two important components. And considering these two important sources of PNC, one can construct the PNC Hamiltonian, which has this form. So I will not go into the detail of the mathematical expression. So the HPNC, total HPNC is going to have the two components. The first one is the nuclear spin-independent PNC, because here the spin part comes with the electron. And the second one is the nuclear spin-dependent component, where the spin part is with the nucleus. Now we can expand further these the wave function and these matrices, and we can work out the expressions. So this is the final expressions we use in our theory paper. So the NSI PNC, which is expressed in terms of this theta W, which is the weak nuclear charge, and NSD PNC, which is expressed in terms of this mu W prime, which is, we call it the weak magnetic moment of the nucleus. And the important difference between these two is this. Here in the case of energy PNC, you have the nuclear spin sitting up, which makes the calculations more tedious. Now, the idea is the following. So PNC observable. So the idea about this work is that, so if you have this, if you don't consider the PNC interactions in atomic calculations, then your eigenstate is the eigenstate of this, the Hamiltonian, what we call this Dirac-Coulomb Hamiltonian, or the remaining interaction other than the PNC. And in that case, this Hamiltonian commutes with the parity operator. So the eigenstate of Hamiltonian, the psi I, they are also the eigenstate of the parity, and hence they have the well-defined parity. Now, if you calculate the electric dipole transition between the same parity state, let's say psi I to psi f, there are two different states, but at the same parity, then this dipole transition is not allowed because it is dipole transition is an odd parity transition. On the other hand, now if you consider the PNC Hamiltonian, the one we just talked about, we consider that in atomic calculation. So the total Hamiltonian is going to be a Dirac-Coulomb Hamiltonian plus HPNC. And now this total Hamiltonian does not commute with the parity operator. And hence, the eigenstates of this total Hamiltonian, they no longer have the definite parity. So their kind of parity is mixed. And now if you calculate the same dipole transition between two mixed parity states, then that comes out to be non-zero. So this essentially actually this E1 amplitude between the two mixed parity states is our observable or theoretical observable, which we look forward to calculate it. And this we call it the parity violating electric dipole transition amplitude. So just to give some more idea about that, so what we can do is that using the first order many body perturbation theory, we can work out the expression for E1 PNC, and that looks like this. So if I can explain a few terms, so now it has this two terms, this and this. In the first term, you have this PNC matrix element, which is between the initial state, which is 1s0 for YB, and this intermediate state. So they are going to be essentially the P's, P states. And then you have the dipole matrix element between the intermediate and the final state, which is 5d6s 3d1. In the second term, the dipole and HPNC matrix, they are switched over. Now, the important point here is that, as Vijaya mentioned out that the idea about this kind of work is that what we do is that we theoretically try to calculate this PNC observable, E1 PNC, very, very accurately. And then there are atomic experiments, very, very accurate atomic experiments, like what Professor Budkar does. And then we compare these two, and then we extract some parameter P from this comparison. And these parameters, they're bound or upper bound in standard model. So we compare this parameter P, the one we extract from the atomic theory and experiment combinedly with the high energy or standard model parameters. And if there is a difference, then we say that it is an indication of some new physics beyond this in the model. So the point here I'm trying to make that for a meaningful extraction of this parameter, or for a reliable parameter P, this E1 PNC should be very, very accurate. And to get this E1 PNC very, very accurate, these states, psi I, psi n, and psi f, which are many electron states, for example, YB, it is going to be a 70 electron system, so 70 electron wave function. So these have to be calculated very, very accurately. So that's what we do. So we use couple cluster theory. In fact, we develop this theory and codes in our group to calculate these many electron wave functions very, very accurately. And then we use them to calculate the parity violating amplitudes. So now I'll just take a few minutes to explain what we do in terms of computational methodology. So as we all know, so this YB, for example, is a kind of a quantum mechanical system of interacting electrons. And if you're looking for a quantum mechanical description of the properties of the YB, we need this quantum mechanical wave function psi I and the energy, which we get by solving this Schrodinger equation, where HDC is the Hamiltonian of the atom, and that is given like this. These are the kinetic energy terms. You have this nuclear potential, and this last term is the electron interaction term. However, the problem here is that for a system like YB, this Schrodinger equation is not solvable exactly, or the exact solution of this equation is not possible. So what we do is that we invoke or we apply the approximations, and we use the idea of independent particle approximation, which tells us that the electrons in an atom, they move independent to each other in an average field, which is created by nucleus and the remaining electrons. And this average field, in our case, we use as the Hartree-Fock potential or Hartree-Fock field. And with the help of the Hartree-Fock field, what we can do is that we can separate the entire quantum mechanical space or quantum mechanical Hilbert space of the atom into two components. One is this, what we call this solvable part, phi I. So they are the Dirac-Fock or the Hartree-Fock state. They can be solved exactly without any approximation. And then this correlation part of the wave function, Q acting on psi I. So correspondingly, we can separate our Dirac-Coulomb Hamiltonian into two parts. One is this mean field approximation or the mean field Hamiltonian, H0, and this is the residual Coulomb interaction, which treat as the perturbation. So the idea here is that if we solve for this Hartree-Fock wave functions or the mean field wave function using Hartree-Fock theories, and then we can construct a exact wave function, or we can derive the exact wave function from the Hartree-Fock wave function by applying certain operator, some operator, which we call is a wave operator. Now, this wave operator can have different form in a different theories. For example, it can have the one form in the many-body perturbation theory. In CI or configuration interaction, it can have one form. But what we do is that we use couple cluster theory to construct this wave operator. And the reason for that is the couple cluster theory is one of the most accurate many-body theories for atomic structure calculation. So the way couple cluster theory works is a very simple idea. What we do is that you have this core electrons. Let's say they are the field electrons, occupied electrons in the case of YB. So what we assume that these electrons, they are going to interact with each other by a Coulomb repulsion. And these, because of the repulsion, they are going to excite it to the excitation. They are going to excite to the excited states. So other way of saying that, if we incorporate the electrons in the excited state in our calculation, we are going to include the electron correlation. So that is the idea. Now, in principle, what can happen is that one electron can excite, two electrons can excite, or all n electrons can excite from an atom. But what happens is that since Coulomb operator is a two-body operator, the dominant contribution to the physics or the properties of the atoms, that is going to be, that will come from the singles and double excitation. So in most of the calculations, what we do is that we restrict our calculation up to singles and doubles. We also incorporate triples in some approximate way, but mostly we restrict ourselves up to singles and doubles. Now, once we have this operator, we can excitation operator, we can construct this wave operator, omega is equal to exponential O, and then we can have this exact wave function psi, which is expressed in terms of the exponential this excitation operator acting on phi. Now these excitation operators are the unknown which we have to get, and that we get from the coupled cluster theory. So now depending on the system, for example, let's consider the closed cell system, what Vijay was referring to, or one valence system, or even the system like YB, which has the two valence electrons. So this coupled cluster formalism is going to be different, because theory will get more and more complicated, and then we need to really work out the mathematical algebra very, very systematically. So in our group, in collaboration with Professor Dilip Pangone, we have developed a series of methods on coupled cluster theory and codes as well. And some of them we have published. For example, this paper is about a photon code on relativistic coupled cluster theory for closed cell and one valence system. So this is there in CPC. One can download and use it. So this is up to the closed cell and one valence. But remember, our system of interest is the YB, which is a much more complicated atomic system in terms of electron correlation. And the complication comes from the fact that it has these two valence electrons. Now, if you consider this energy level diagram for YB, so there can be different type of excitation. These core electrons can excite to the valence, or they can excite to the virtual. And these valence electron can go to the virtuals. Maybe one can go at a time, or both can go together. So depending on this, what we do is that we separate these excitations in different sectors. So we talk about the first closed cell sector, which is taken by these operators T1 and T2, and then we talk about the one valence sector, which is taken by this, which is taken care by this operator S1 and S2, and then the two valence sector where both valence electrons can excite to the virtual, that is taken care by R2. And now these excitation, essentially what he's doing is that one electron is getting annihilated from here and created here. So in second quantized representation, these operators can be represented like this. For example, T1 is expressed like this. So this small a means that one electron is getting annihilated and created to the p state, and the probability for that transition is TAP. Similarly, all these other operators. Now what happens here is that since these operators are expressed in terms of the creation annihilation operator, if you put into the coupled cluster expression or the wave function, the expressions get very, very complicated. So we don't really work in terms of the mathematical expressions, rather we work in terms of the diagrams. And these diagrams we call it the Goldstone diagrams. So for example, the T1 operator is represented like this. So this core is annihilating, particle is creating. Here two cores are annihilating and two particles are creating. Here one valence is annihilating and the particle is creating. Here both valence are annihilating and they are going to the excited state. So considering these operators which are applicable to two valence, we can certainly write the wave function, this psi VW. So this is the wave function like YB system. It can be 3D1, the one we are interested in. So that is going to express in terms of exponential t, and this one valence operators, and then this two valence operator, and this is entire operator. They are going to act on the Dirac-Fock state. They will give us the excited states, and so that is the idea. So the way we get these operators is that by solving the coupled cluster equations, what we do is that we substitute the value of this wave function in the Schrodinger equation, work out some mathematical algebra that we call it the coupled cluster equation, and by using program we solve it. At the result of the solution, we get these operators put here, and Dirac-Fock state we already know, so we can get the exact wave function, which we can use for the E1 PNC calculation. So that is about this. Okay, so as I said, we work in terms of diagrams, and so far at the various stages of our theory development, we have calculated and coded roughly about 1,000 diagrams. And this slide shows the calculation or evaluation of one diagram. So this is called the 4-particle diagram, and you can look it. It is not very complicated diagram, but this is how we do the angular momentum calculation. So the expression or the value of this diagram is this one, the last line. This is what we program. All right. So now the region, I said that the YB is a difficult system to calculate because it has the complicated electron correlation nature. In terms of the coupled cluster theory, it also has the challenge, and probably that is the region that not many implementation of coupled cluster for YB-like system, what you call the multi-reference coupled cluster. So the major hurdles with the multi-reference coupled cluster theory are the following. So the first one is this model wave function is not well defined. For example, if you have the closed cell system or one valence system like Vijay was mentioning, so there we know what is the Dirac-Fouquet state. But in the case of YB, in some cases, the Dirac-Fouquet state is not known. So what we do is that we do the linear combination of all the possible states, and then we realization of the effective Hamiltonian. We construct the effective Hamiltonian in the space of that model state functions, and then we get these coefficients C1 and C2, and then we construct the Dirac-Fouquet state. If I can give you the example, for example, consider this YB. So consider the configuration 6s and 6p. So it has this 3p0, 3p1, 3p2, and 1p1 ASFs. Now, if you look into this 3p1 and 1p1, they have the same J. So they are going to mix. And the mixing is going to be like this. So the actual 3p1 wave function will be the linear combination of the two. Similarly, actual 1p1 wave function will be the linear combination of these two, where these C1 and C2, they are called the weight factors, and they need to be determined. And that we determine by diagonalizing the effective Hamiltonian. So that is one complication we have, one challenge we have in two valence coupled cluster in comparison to closed cell or one valence. The second one is this divergence due to individual states. So these two valence coupled cluster calculations, they often diverge. And the reason for that is this individual states. So what happens is that if you consider this, for example, in the case of YB, we consider these as the valence state 6s, 6p, and 5d, because 6s2 is the 1s0, which is of our interest. 5d, 6s is 3d1, which is of our interest. And the 6s, 6p, they are the intermediate states through which YB PNC transition is connected. So out of these valence orbitals, if I consider all possible two valence configurations, so my model space will have all these 6 configurations. Now, if I include these 6 configurations in my calculation together at a time, then what will happen is that there is this excited state 6s, 7s, which is not the part of the model space, which is a part of the correlation space, but this is below this 6p2. And they have the very close energy gap, or this has a very close energy gap to this 5d6s. And because of this tiny energy, what happens is that coupled cluster calculations, they diverge. So to mitigate this problem, what we do is that we use very selective configuration calculation, and what we call is the quasi-incomplete coupled cluster calculation. And in fact, when we do that, we have to pay the price in terms of accuracy that I will show you when I show the result. Okay, so the last, please remind me when I'm close to the time. Hello?
Yes, I will. Thank you.
Yeah. So please remind me. So now the third major complication is this, because now we know that our states are the total J states, for example, 3D1, 1S0. So we need to have the coupling of the angular momentum. So if you look at the typical coupled cluster diagram, that looks like this. The one is given in this rectangle. They are expressed in terms of single particle state, for example, S half, P half, S half, P half. But these, they need to be coupled. SP half has to be coupled with this P half to get this P0 states. And similarly, 1S half has to be coupled with the 1S half to give us this 1S0. Because these ASFs are of our interest. And this coupling is done at each diagram level. So remember, we have so many few hundred diagrams, and this should be ideally done with each diagram level. And if you do this coupling, then it leads to the complicated angular factor like this. So we need to go towards the various pages of calculations, analytical calculations, and we get these final expressions as a result of the coupling of these single particle states times this coupled state, which we are interested in. So what I'm saying that So since J is the total J is a good quantum number, we need to couple the angular momentum of the single particle states to get the multi-reference state. So this is the one of the other challenge we come across in the two-valence coupled cluster theory. Okay, so now what I've talked about is the two-valence coupled cluster theory, which is needed to calculate the wave function accurately for the Coulomb interaction, or which takes care of the residual Coulomb perturbation. However, if we have to calculate the PNC or even PNC, then we need a theory or the corresponding theory which can take care of the external perturbation like HPNC. Or if we have to calculate the electric dipole polarizability, we need additional theory which can take care of the electric field at the perturbation. And for that, we have additional set of operators like this. So this is what I have talked about to you. No external perturbation. Now, if you have the PNC, then we are going to have the additional perturbation, additional operators T11, T21. Here there is no one. So 1 means here is that it is a tensor operator of rank 1. These are the Coulomb interaction. They take care of the Coulomb interaction. So there is scalars S11, S21, and R21. So these are the additional set of parameters of operators or excitation operators we have to deal with for the PNC calculation. And this, once we have this additional set of parameters, that theory we refer to as the perturbed coupled cluster theory, because it is going to take care of the external perturbation. Now, I can write my perturbed wave function, which is essentially used for the PNC calculation, and that is going to have this complicated expression. So now here is a psi v tilde. Tilde represents the mixing of the effect of the PNC perturbation. So this is the wave function essentially I will be using for the PNC calculation, and that is going to be in terms of this unperturbed T, perturbed T, then you have this unperturbed one valence operator and the unperturbed two valence operator, and then the corresponding perturbed operators. So this is the expression for wave function we deal with. And then again, we substitute this back to the perturbed Schrodinger equation that H Dirac Coulomb plus lambda H PNC psi is equal to E psi. And then we work out this expression for the coupled cluster equation, and then we solve it, and then we get these operators put here and get the wave function. So this is what we are working at the moment. We are working at the perturbed coupled cluster theory for two valence, and which is needed for the YB PNC, and we are very close to complete it. However, for this perturbed theory for closed cell and one valence, as I already talked about, we have gone a very long way in terms of development. So for the closed cell and one valence, we started in 2009. So I was doing PhD with Dilip, KVP Lata was there at postdoc. So we developed this closed cell perturbed coupled cluster theory. And after that, we have gone in a series of development in terms of incorporating the nonlinear diagrams and then the bright QED corrections. And also we have extended to the one valence system. So these papers talk about the perturbed theory for closed cell and one valence system.
So Brajesh, you have 10 more minutes.
2 minutes.
10 minutes.
Oh, okay. Yeah, 10 minutes is fine. Yeah. Okay. So this is what. Okay. So now let's say we have the perturbed wave function. We solved all these mathematical algebras. We wrote the program. Now we have this psi v tilde. Now we want to calculate the polarizability. So now we want to calculate the E1 PNC. So E1 PNC is going to be the this should be the bra vector should be some different state. Let's say it should be psi v tilde xw. So it goes from, let's say, 1h0 to 3t1. So this is the expression for E1 PNC, where this psi v tilde, I have already shown to you, this is going to be the complicated expression. Now you use the bra vector this side and the ket vector this side and work out this expression. There are so many terms are going to be there, and each of them will lead to so many diagrams. So these are the typical diagrams for the two valence E1 PNC. Some of them are the dominant diagrams. So here I've shown this just for the examples, but in actual number, they be maybe more than 200. So these are the diagrams we calculate. And in fact, these diagrams, if you look carefully, they're just electronic components. So this is E1 PNC electronic part. It has, because we have separated out, but the actual PNC diagram will have the nuclear portion coupled as well. For example, if I consider this electronic diagram, so then the actual PNC diagram is going to be like this. So it will have this electronic part, and the nuclear operator is coupled here. So this is the nuclear state, and this is the rank of the nuclear operator. So this is the actual energy PNC diagram in the coupled cluster theory. And as we can figure out now, see here, there are 3 pair of valence lines. The 3 pair of free lines here, 3 pair of free lines here. And essentially we need only 1 pair of free lines. So we need to do the, again, angular momentum algebra calculations to solve the diagrams. So let me spend a minute and see how we show you how we solve it. So what we do that we start with this first, this electronic component, electronic part of the diagram, what is given in the rectangle, and then we couple it. So this X, Y are they're coupled to give J prime, and this VW are coupled to give the J. So the initial state is J, final state is J prime, like 1 is 0 and 3D 1 in the case of YB. And then, so this whatever is there in the closed loop, that has to be evaluated. So evaluate it. So after evaluating, we get the factors, angular factors, like what is written here in the A, which is going to be the function of all these parameters. So it will be 6Js, 9Js, and some phase factors, which are not written. And then we'll get this coupled electronic state, J is going to J prime. And then even the nuclear is being coupled here as well. This is not over it. Now we have to couple this J and I to give the hyperfine, because E1 PNC is between the 2 hyperfine states. So this J and I have to couple, J prime and I have to couple. So now we get like this. So we couple this J with I to give the F, J prime I to give its F prime. So the initial hyperfine state, final hyperfine state, and in addition we'll get the phase factor A2. So now this A1, A2, they are the phase factor. They are going to be a combination of 6Js, 9Js, complicated expression. And then finally we get this, the free part, where this one hyperfine state is going to the other 5 hyperfine state through this interaction. So this is the typical mathematical works we do, and we do it for all the energy PNC diagram. You can assume there are 200 diagrams. So that is what effort is needed for the NST PNC, like YB system. Now, so I'm close to my end of presentation. Now what I'm going to show you that very preliminary results, some preliminary calculations we have done for YB. We have a scope for the refinement, and we are working on that. So now first I would like to share with you the excitation energy. So let's see, so this is the ground state 6s2. And if you can see here, now see this, our calculated excitation energy, or the 2 electron removal energy rather, it is in very good agreement with the NIST. The error is 0.1%. So this is very good, I would consider, because it's a ground state. However, if you add the excited state configuration, then let's say at the 6s6p, then the excited states, they have relatively large error. For example, the 1p1 has the 7% error, and that is large in comparison to the ground state. Now, if you add further the excited states or the excited configuration, let's add now the 6s5d, which has this 3d states, because we need to have 3d1 in our calculation, because the transition is 1s0 to 3d1. So then the error to the energies for the P's are all 5 increase, and these D's, they have this about 8 to 10% error. So this may sound a large error if you compare with the cesium-like system, but in reality, considering the nature of YB, it is not bad. It is not bad in the sense that if you look into the literature, except in the calculation where people do the refinement of the fitting of the energy, if you look into the calculation which are purely ab initio calculation, this is the accuracy, a little bit smaller accuracy you will find in the literature for YB-like system. However, there is still scope for us to improve. So we are yet to include the bright QED correction, perturbative triples correction to these energies, and more importantly, the energy from the high, the configuration from the high energy. Because remember, 6p2 is still left, and then 5d 6p is still left. So those we can include to refine this valence-valence correlation. The reason for this discrepancy is the valence-valence correlation, and that can be taken care when we incorporate the high energy configuration in our model space. That is what we are working on at the moment. The next result, I can show you some preliminary results on this electric dipole transition amplitude, because they contribute to the PNC. Because if you remember that even PNC experiment, the expression, so the dipole transition between 1s0 and 3p1 and 1s0 and 1p1 will contribute there. And in fact, also the dipole transition between 3p1 and 3d1 and 1p1 and 3d1 will contribute there. However, the dominant contribution, about 90%, comes from these two, 1p1 and 3p1, because that 1p1 is the one which mixes very strongly with the 3d1 because it has a closer energy level. And if you look carefully here, so now our result, for example, the 4.3 is in the range of the previously calculated transition amplitude. For example, this one, 1 is also close to the other theory values. However, I must mention that none of these theory values are using the focus space coupled cluster. They are using the either CI plus MBPT method or multi-configuration Dirac. So we have the better chance to improve it and contribute to this NSD-PNC. I can show you this, the preliminary calculation magnetic dipole hyperfine constant. So if you look at this 3p1, 3p2, 1d, 3d1, they have this error about 10%, which is consistent with the error in the energies. But if you look for 1p1, which need to be optimized well for the PNC, this has here about 46% error, and that need to be taken care. However, I would like to mention that 1p1 is always tedious to optimize, and the one example is here. If you look into the recent, so by these experiments are a little bit old experiment. So if I can use some recent data, so for example, this one is for the YB171, and this paper is by Juba and Victor Flambau. That is what I talked about, 2011 NST-PNC paper. So here in this paper, they have calculated this magnetic dipole hyperfine constant for 1p1 state. That is, the value is -819. And this experiment, which is relatively newer experiment in 2005, it is -214. And the difference between these two is 282. So that is from CI plus MBPT. If we look into our calculation, it is about 151 or so. So what I'm trying to say that 1p1 are in general these multi-reference states, then they need effort to be optimized. And that's what we are looking forward to. That's what we are doing. This is the polarizability. It's the ground state polarizability of the YB. And if you look, so here we start with the Dirac-Fock calculation and we go on incorporating various level of electron correlation. We use perturbed coupled cluster theory, then we add the perturbative triples, then we add the bright and QED, and also we imply very, very large basis set. So the coupled cluster code we have that can afford, or that using that we can do calculation up to, let's say, 250 basis, Gaussian basis, and which is a kind of a good that we can even incorporate the small contribution from the high symmetry orbital. So for example, if I show this, so our recommended value for the YB 1s0 polarizability is 142 ±4. And just for comparison, I have listed here some of the important results, essentially the all coupled cluster results, just to show that. So now it is within the range of the previously calculated values. However, see here, there is a large variation. The smallest value is 136 and the largest value is 152. They both are using coupled cluster CCSDT, and ours one is within this range. So the reason this good, the ground state polarizability is reproduced well, probably because the ground state wave function, as we saw, that was calculated accurately. All right, so now one can ask the question that what is about the polarizability of the excited states for the YB? Are the excited states of the YB-like system, like strontium, is also good for the atomic clock? So that is what we are working on. So along with this NST-PNC, we are working on the excited state polarizability for the YB-like system as well. And in fact, if we look in terms of very closely in terms of theory, the polarizability diagrams and the PNC diagram, they are same, except the difference is that in the case of PNC, we have the nuclear spin. So once we are able to solve the NST-PNC YB, we will be able to calculate the polarizability of the YB excited state as well. All right, so this is my last slide. So, okay, so I saw here some very preliminary result for the electric dipole transition parity violating amplitude, that is between 1s0 and 3d1. That is the main goal for the goal of the presentation or goal of the calculation. And this is what is measured by Professor Budkar group. So now we have used MBPT. Couple cluster still, we are working on that, and we are hoping that next 6 months or so we'll be able to complete it. So this is our result, MBPT result. And I have written here 2 results. One is from the Dilip. This is using the CI. And the other result is the most recent, this 2012 paper by Porsev and Kozlov, that is CI plus MBPT. So in terms of magnitudes, our MBPT result is close to this, in fact, both of them. And in terms of sign, our one is matching with this more accurate CI plus MBPT calculation from Porsev. However, there is a lot more scope for us, a lot more work for us, in fact, in the future to implement the coupled cluster to calculate it. So that is what we are working at the moment. Okay, so I come to the end of my presentation. So in summary, I have to say that, so at the level of closed cell and one valence, I think we have gone a long way. We have done series of developments for unperturbed coupled cluster theory. At the moment, we are working on perturbed coupled cluster theory for 2 valence. We are able to calculate the unperturbed properties like excitation energies, event transition amplitude, hyperfine constants, or any multiple moments, etc., where we don't need external perturbation accurately using 2 valence coupled cluster theory. For YB in particular, the properties results I showed you, they are very, very preliminary from our end, and we know that where is the scope to improve it, and we are working on that, and hopefully next 6 months or so, we will be able to refine those results. Okay, so with that, I think I'll stop. So my collaborations and funding, so I have mentioned here, and these are my students. So essentially the students which are there in this red box, they work in this atomic physics. So Ravi graduated his PhD. Now he's at the University of Zurich. He's doing the postdoc. The work I presented is from Suraj Pandey. He works in YB-PNC. That's what I presented. This student Palki, she works in atomic clock. So that is also the atomic physics area. Remaining students, they work in the condensed matter physics, where we look into the physics of condensed matter system like ferroelectric, ferromagnetism, topological insulators. So other aspects of work, we look into that, which I learned from my postdoc. So I'll stop here. Yeah, thank you. And yeah, so before, one thing again, in the final, I'd like to congratulate Professor Budkar on his 60th birthday. And we look forward to interact with him more. And also we look forward to his expert guidance in what we are doing at IIT Delhi. Thank you.
Okay, thank you very much, Brajesh, for a very detailed description of your work. And this certainly is an important area, I think. And, Professor Budkar has observed ytterbium, parity violation in ytterbium. I think the anapole movement will probably happen in the next few years or a bit more. So I think this will be very interesting in the future. So any other comments, questions?
I'm sorry, I'm always barging with comments and questions, but I do have some comments.
The valuable.
Rajesh, thank you so much. This is very exciting developments, and the signs are always trickier, right? Because of conventions and so on. But it's good. It's good that there's it becomes clear. What the right science is. That's very exciting, actually. I have a comment about the history of parity violation. And can you show that one of the early slides where you I guess now this is a long time. Soon going to be 50 years in a few years since the discovery of parity violation, so it kind of gets far away. But you know, when I was a student, I was working with Professors Barkov and Zolotaryov in Novosibirsk, and they were the pioneers of this business. And so I basically grew up hearing stories, and it was very dramatic in 1977 because indeed the first two groups. So as you said, you know, Zildovich estimated parity violation was considered to be a very small effect, and then in 1974 the Bushias discovered the Z-cube enhancement, and I like to say it was like you know, starting pistols that several groups started to do, including the Bushia group, and the first people who claimed to have crossed the finish line were the groups of Pat Sanders at Oxford. Banu knows this story extremely well, of course, and Norval Fortson in Seattle. Unfortunately, they both reported results consistent with zero and inconsistent with the predictions of the standard model. And that was a bit of a strange situation. But at that time, the Weinberg-Salam was not called standard model yet. So Hriplovich, for example, one of the theorists, he said, well, I'm not married to Weinberg and Salam, so maybe it's something else. And at that time, the Novosibirsk group of Barkov and Zolotaryov, they reported now a result consistent with the standard model, confirming. And so while they were not the first to report the result, they were the first to report the non-zero result. And then for a little bit, you know, for a few months, it was a bit of a sort of uncertainty because there were two groups claiming zero, one group claiming standard model result. Then Professor Cummins at Berkeley, and so I was very lucky, you know, because I worked with the first guys who observed parity violation, and then went to work with Professor Cummins, and he was, you know, the first guy to observe parity violation with a slightly different method than in thallium. And then after eventually all the groups, the Oxford group and the Seattle group, they also saw non-zero results. Actually, there are some factors of 2 unresolved till this day, eventually with that particular transition, but that's not important. The important thing is that, of course, a parity violation is consistent with the standard model. So that's one comment. So if I were you, I would replace the Sanders at always Barkov and Zolotaryov.
Okay.
Yeah.
Okay.
But of course, Pat Sanders was an extremely important player in this field. There's no doubt about. Okay. Do you agree, Bano, with my version of the story?
Yes, I do. But as you said, probably there's a discrepancy of some factor between the results of Barkov and Zolotaryov and Sanders and Fortson. But yes, I think Barkov did indeed, I mean, report the first zero result for parity violation atoms. There's no question about that. Yeah. Yes.
What was the system? Which bismuth?
That was bismuth. That was
bismuth.
the
bismuth.
Now I forgot 618. I forgot the exact wavelengths.
Yeah.
Or 650. Oh my God! I thought I would never forget that wave. Anyway, somewhere red wavelengths. Visible.
Could have been 648 or something?
Yeah, 648. You're right. Okay. Bano actually has an amazing memory, remembers everything. Yes, good. So anyway, my second thing is not even a comment, it's a question. So you know, like when experimentalists write proposals for doing some spectroscopy, they often write that, well, this would be useful for testing, this kind of measurement will be useful for testing many-body theory. So my question for you is, so now there is relatively new data on isotope shifts in the terbium that we discussed before. And I wonder if you can use that to test your calculations a little bit. So here, for isotope shifts, I think the mass shifts that can be separated with the King plots, they can be sensitive to, you know, electron correlations. And the field shifts are very sensitive to configuration mixing. So naively, as an experimentalist, I would think this would be a very good test of your model if you can calculate those.
Yeah, certainly we can do that. In fact, we did similar calculation for the strontium last month. So YB we can also do. So there is a group, this Umakant Rapol at ISET Pune. So he's working on this strontium atomic clock. So he has done this isotopic measurement there. So we did isotope shift calculation and King plot analysis for him. So yeah, so for YB also we can do it. It's the same. It's a similar system.
Fantastic. Yes, and then the data are available as we discussed.
Yeah.
Our recent measurement and then the Japanese group measurement, which is even more precise. So we are talking about isotope shift measurement now probably at the level of a few hertz.
Yeah. So these are two papers we are talking about, 2019 papers. One is Nature, another is
no, 2022.
Okay. Then I think
isotope shift, not isotope effect in.
Okay. Yeah, this is about isotope variation in PNC. Oh, that's isotope shift. Yeah. Okay.
Isotope shift, yes.
That we can calculate
as a complementary test of theory.
We can calculate it.
Yeah, because it would be sensitive to, like I said, to some things that maybe other things are not so. So, for instance, the mass shift is very sensitive to electron correlations, right? Probably in the core.
Yeah.
And so if possible, would very much like to have a copy of your slides if that's possible.
Okay, I'll email it today, just after.
Yeah. Thank you so much.
Yeah, thanks. Yeah.
Okay, any other comments, questions? Okay, if not, I mean, thank you very much, Brajesh, and Dilip also. And this is great work. And I think, we expect some really great results in the future. Okay, all right. So
yeah, thank you. Thanks.
Yeah. So we'll move on to the next talk that is by Tanmoy Basu on. Okay, Tanmoy, please. Yeah.
Am I audible?
Yes.
Okay. Thank you, Professor Das, for allowing me to give a presentation on this auspicious occasion. And let me first congratulate Professor Budkar for his 60th birthday anniversary. So fortunately, I have been given this work to design the website. And when I was designing the website, I came to know that my previous speakers mainly were from AMO background, which I am not. So please bear with me in that respect. I am from condensed matter background, but I must say that there is just once we had a discussion with Professor Budkar through Professor Das, and that is on Zoom. I think if I'm not wrong, the date was 20th July, around 12 noon. So yeah, so the idea mainly which motivated me, so it is related to the ENVI Center, which is another field that Professor Budkar works, and he's one of the pioneers in this area of nitrogen vacancy-based sensing applications in diamond. So there is one work that Professor Butker's group has published in 2017, which published in NatureCom, and there they have done, or they have shown, that kind of twofold or two orders of magnitude improvement in the sensitivity using kind of nanostructured chip where you can plug in the NV centers and do the NMR applications. So this is kind of the main motivation. So let me start with this background, how I got motivated further from this work, and if there is any overlap with my current ongoing works that I have been carrying out in TCG based. So let me first share the screen. Okay. All right. Everybody can see it. Now, so to start with, the title of the talk is Engineering Defects for Quantum Sensing. By engineering means basically to play with the defects that you can form in the material, host material. For example, in this talk, I'll be talking about mainly diamonds, but there are other materials also which are coming up as potential candidates for quantum sensing, which are also very important. So now to start with, I think this is the picture of general natural diamond that everybody know. So mainly when we talk about diamond, we care about the clarity, carat, all these parameters, and we don't want any defect into this material. So that is the kind of benchmark for a good quality diamond. On the other hand, in some cases, we need those defects or imperfections in the diamond crystal. And that's where nitrogen vacancies play a very important role. For example, this is one of the picture where you have nitrogen vacancy centers, and then you excite with green light, and in turn you are getting red for photoluminescence. Now, this is very important in terms of if you look this system a bit more critically in microscopic level. So the diamond lattice is made up of carbon atoms, and then you put, by some means, you put this nitrogen and create vacancy, which forms a pair, and then behave like an artificial atom. And the energy level structures, which is very similar to this, is very important because it gives spin dependent fluorescence. So that is the main area which is utilized for quantum sensing applications. Now, this photoluminescence, they have I mean the excitation we normally do with the green laser, and then it emits light over a broad range at room temperature in the red region, starting from 630 onward to close to 800 onwards, depending on the defects. Now, these NV defects, there are different categories of NV defects or nitrogen vacancy defects. They can be charged, they can be neutral as well. For particularly this kind of fluorescence or spin dependence fluorescence application, where we use this property for magnetic sensing application, we use nitrogen vacancy, which is negatively charged. So negatively charged nitrogen vacancy centers that is being used, which shows this special effect, which is called optically detected magnetic resonance. So basically, when you use this effect, or you pump the energy levels with the ground state from excited state with green laser, then the excited electrons come back to the ground states. They emit light in red region, but there is another pathway, that is single state, which is non-radiative, and mix the kind of competition between these two radiative and non-radiative transitions give rise to this magnetic sensing application. Now, we can also use microwave to do this resonance structure or resonance excitation, where you can excite the electrons in the ground state to the higher excited states using 2.87 gigahertz. And when you are doing this, you can actually during your measurements, you can sweep the microwave frequency over this range of frequency below 2.87 and go beyond past that, and you see a dip in the photoluminescence intensity, and that's where you can basically know that yes, you are doing it right. You are doing the proper initialization of your structure. So this is kind of basic, and then this whole system is sensitive to external magnetic field. When you bring this external magnetic field, the ground state MS1 state basically splits into two because of the Zeeman splitting, and then the peak in the optically detected magnetic resonance becomes two more peaks, and then from the separation between these two peaks, you can actually calculate the external magnetic field. So the magnitude of the external magnetic field. So so that is basically the background of the how you do quantum sensing using NV center plugged inside the diamond lattice. Now there are few problems with this system. Although it seems very nice, there are still some bottlenecks, which I will come later. But before going to that, I would also like to show what we are doing in TCG Crest. So we have fairly large group in TCG Crest. There are theory activities going on, also experimental activities going on. In theory, quantum computing, quantum algorithm-based work are going on. In experiment, we have three platforms. One is quantum computing based on superconducting qubit architecture. Then there is a quantum sensing activity also. In these two, we have neutral atom based activity, which is being done by Dr. Vaishik Acharya. And then I am also involved in two aspects. One is photonic integrated circuits and NV center based magnetometry application. Right. Now let's start a little bit with photonic integrated circuit. By photonic integrated circuit, what I mean is it's a normal optical circuit similar to electronic circuit, but you miniaturize it on a small chip, maybe 1 centimeter or 2 centimeter in dimension. The application is there are many applications of this architecture which are listed here. Some of them are also linked to NV center magnetometry, quantum light source development, like single photon source development, and quantum sensing. So our group mainly is involved in quantum enhanced sensing application using photonic integrated circuit architecture, and also with NV center magnetometry, where we can use photonic structures to enhance the sensitivity. That's the approach. All right. So now come back to the NV center. The NV center is why we are more interested in diamond, because in modern fabrication technology, you can actually fabricate wafer scale electronics and photonics using diamond. So you have optically addressable spin qubits also, which I have just talked about. And then you have also long coherence time at room temperature, which is very important for diamond NV centers. Now, you can create NV centers by different approaches. Generally speaking, there are two approaches. One is top-down and another is bottom-up approaches. The top-down is, I think, is referred in many papers. So by top-down means you first grow your diamond and then you create the vacancy and the implant. You do implantation with nitrogen and create the NV center. So this is post-growth process in top-down. While you can also do the other side, that means you can take bottom-up approach. That means when you are growing diamond on a seed diamond layer using CVD method, chemical vapor deposition method. You can also create a single molecular level NV center with very high precision in this kind of diamond material. So this bottom-up approach is comparatively new, and I think people are also exploring to grow very high quality NV diamonds. All right. So now, when you create diamonds, NV centers, and they emit lights, but problem is that you emit it very in all directions. So the sensitivity of this quantum sensing application or the magnetic field sensing depends on also kind of how much coupling you can do or how much efficiently you can do this light extraction. So if you can really couple the NV center with your proper detector very precisely, then you can actually enhance the overall sensitivity of the system. So here are some examples schematically shown. You can use a cavity kind of approach that I think Professor Rangwala previously mentioned. You can also use take help from the thin film based structures. So you have a very thin layer of different material, different core material which has higher refractive index, and then you coat it with material which has lower refractive index. That will give you kind of waveguide structures, and you can guide light very precisely. Of course, your fabrication has to be very good, because the whole coupling and the insertion loss all can be, it depends on different parameters like sidewall roughness and other things. So the precise fabrication of this kind of photonic structures are very important. Now, we have been working in similar structures for some time, and we could now fabricate few structures. One of them is like Mach-Zehnder structure, Mach-Zehnder interferometer, which you can see on screen. So the first image on top is basically the finite element simulation that we have done to see whether the modes that we are coupling is actually propagating into the waveguides, and you can see transmission in the output port. We have confirmed that yes, the dimension and the overall structures, the bends, everything is correct, and we could guide the light through this structure. In the bottom part, we have fabricated structures, which is kind of polymer structures, SU 8 based structures, which shows very low loss normally in the telecom wavelength range, that is 1550. We are also working on different kind of other photonic structures like ring resonator, Y splitter, different kind of other structures, and we are optimizing all these elements mainly for the quantum enhanced sensing applications, where we can actually guide or couple single photons into these circuits and do some kind of enhanced sensitivity application for some application. So this is kind of the background of the photonic integration part with the diamonds, which we want in future. So basically, which I will explain later. But before going to that, I would also like to say something about some of our recent results, which is based on the implantation approach that I have mentioned in the top-down approach for fabrication of the NV centers. Now, so the approach that we have taken is ion implantation. What we have done. So this is basically a generic part, how ion and matter interacts. So when ion impinges on a surface, there are multiple phenomena which happens. So you can see all this happens. You can create defects. You can create sputtering. You can emit atoms from the surface. There are multiple things going on based on the energy of the ions. Now, ion implantation gives very precise control over how many number of ions that we want to implant in the material, and also the depth resolution is very high. So you can tune the energy of the implanting ion, and then you can go to a certain depth that you want to probe basically inside the material. So, and it's a low temperature process. In some cases, you don't need to go very high temperature for doing a phase changing application. So there are these are the some of the applications that ion beam delivers. But it is also depends on how much dose you are putting. So if you put too many ions in a material, it can get deformed or it can get amorphized. So that has to be judiciously taken care of. For our case, what we thought of, we want to have so basically we want to do kind of a study where we can enhance the sensitivity of the diamonds. And for this application, what we have chosen is called nanodiamonds. Instead of a single crystal diamond, we have taken small pieces of diamond, which are of the order of 100 nanometer in size. And then we want to create NV centers or the vacancies very close to the surface. So very close means within 5 nanometers from the surface layer. And for that, what we have done is we have a kind of home-built setup, and then we can create beams using microwave sources of different ions, different gaseous ions, and then we can extract the beam, and we can put the beam onto our surface of the target material. Here we are using nanodiamonds, which are drop casted on a silicon wafer, piece of silicon wafer. This whole irradiation process is done at room temperature and at high vacuum of 10 to the minus 8 millibar. Now, the ions that I have used in this process is helium ions, and I should mention here also that in this work, these nanodiamonds already have some amount of nitrogen vacancies, which is of the level of 3 ppm amount. And my goal is to actually, can we enhance this 3 ppm level of NV centers by some means. So sometimes if you are increasing the number of NV centers, the sensitivity is also proportional to the number of NV centers available. So that's the idea. So for doing that, we didn't implant nitrogen, but we implanted helium at very low energy, which is 500 electron volt. So if you see the simulation, the range is including straggling is within 4 nanometer or maximum 5 nanometer. So we are very close to the surface. Now, when we do implantation very close to the surface, the main application that we can think is doing a kind of biological sensing application, where you need to be very close to the analyte or the biological protein that you are detecting. So for that, the NV centers has to be very close to the surface layer. Now, when you are putting NV centers very close to the surface layer, there are different problems, because with the interaction of the environment and their charge switching mechanism which happens. So because of those problems, the overall sensitivity also goes down. So this study will also give us some idea about whether we can retain those charge states at NV minus instead of NV zero, converted into the NV zero. So these are very preliminary results that I will show. So this is just a scanning electron microscope image of this NV centers that has been dispersed on silicon wafer. And if you measure the sizes, is about 100 nanometer in diameter. The image is a bit blurry because of charging effect. So I have to coat them with a metal layer, which is not done in this case particularly. We have also done PL studies of these samples. What we have done basically is a variation of the doses or the fluences that we have used for irradiating these diamond samples. And out of those doses, I have shown here in the right side the photoluminescence. This is not confocal. This is normal photoluminescence study. And so the black curve, which is probably you can see has a very small intensity, which is as prepared. That means the drop casted nanodiamond layer. And after irradiation, with helium, we are getting an enhancement of 2 peaks mainly. One peak is also blue shifted. So this is very preliminary result. We have just got it maybe 1 or 2 days back. But I wanted to put it because I wanted to have some comments on particularly this spectra from Professor Budkar as well. So yeah, so now the work that I mentioned in the beginning from Professor Budkar's group, which is done with NV Center on nanograting, implanted in nanograting layers. Now, in this scheme, what I am planning is to use the nano diamonds, which I have shown earlier, and implant them with different ions, and then you manipulate them either by lithographically, or you can do it with surface probe based techniques, and couple them with a cavity. Now this cavity will give this parcel effect, and probably it will lead to enhancement in the emission intensity, which in turn can also enhance the sensitivity close to the surface layer. So that's kind of the work that I'm planning in future. We have fabricated these kind of grating structures on PMMA very recently, and then we are now trying to do this manipulation at nanoscale using these nano diamonds. So this is kind of the layout of what we are planning in our lab. There are 2 parts basically of this experiment. One part goes for so the left part, if you have it axis at this, so the left part is mainly for the single photon characterization part, and to couple the light to the photonic circuits. And the left part is mainly planned for the ODMR spectroscopy, continuous wave. So yeah, so this is kind of a short overview of what I am planning. Yeah, of course. Yeah, this is kind of the overall summary of the what I have said. And some of the collaborators' names are here, mainly who are contributing in this previous work that I have shown is Professor T. Shoms, whose lab facilities I am using for this irradiation purpose. Then Dr. Joy is helping me with the irradiation experiments, and Dr. Gautam Pramanik for the photoluminescence measurements. The photonic structures is made with the help of Dr. Shubhadeep Datta from Cultivation of Science. And we are also collaborating with Professor Kosturi Shaha from IIT Bombay for the characterization purposes. My project, I should also thank my project associate Midhun, who is doing all the simulations work and kind of helping me to understand more into this domain. With this, I think I'd like to thank and I would like to have any questions. Please.
Okay, thank you, Tanmoy. I mean, for a very nice overview of what you're doing. So, any comments or questions?
Tanmoy asked me a question there, and unfortunately, I don't know. My answer is I don't know, because I don't have experience with helium implantation. Okay. Do you have any idea of the origin of this second peak, or both of them, to the for that matter?
I think the second peak, I mean, it's confusing from the literature. The second peak is probably from silicon vacancy, which is created. I don't know exactly how.
Sorry, isn't the silicon vacancy at 737, 738?
Yeah, this is 766, close to 766.
So why do you say it's silicon vacancy then?
Because at this range, only this silicon vacancy, which is kind of getting very close. I don't know. This is very preliminary idea that I searched from the literature.
And the first one?
The first one is probably from NV negative center. and there is a blue shift for the red one. So this red one, there is a blue shift of about about 40 nanometer.
So blue shift. Well, that one is supposed to be at 630.
Yeah, 670. Yes, this is getting at 670, close to 670. So for NV negative, you should get it at 637 nanometer, ideally.
Yes.
But I think that is probably hidden somewhere here, since it is done at room temperature. So we don't see the cleared line for the 637.
I know who knows probably what this is. Is Jan Meyer. You know Jan Meyer?
Jan Meyer, okay.
Yeah.
Actually,
yeah.
He's working with nanodynamics.
In Leipzig.
Oh, Leipzig.
So, yeah. He's he's doing a lot of this kind of implantation things. Difference. He's like the real guru of this business, so he would know.
Okay, I see. Okay, thank you. I will check it in detail, and the idea is to see whether we can get any ODMR from these samples after implantation. Basically, helium is chosen because it doesn't create too much damage, but also create knock-on vacancy creation. So it's that's the idea. I think in your work probably you have used neutron irradiation in the NatureCom work. So that's kind of the thought. Okay. So any other question?
Okay, if there are no, questions or comments, thank you, Tanmay, for a very interesting talk. And so I'd like to thank all the speakers once again. And now we've come to the moment we've all been waiting for. This is to hear some words of wisdom from Professor Budker. Okay, so Dima, we now like to invite you to for some comments, observations, advice.
Okay, I wish I had some wisdom, but anyway, I'll be very, very brief. I just want to say that I'm very, very deeply grateful to all of you for taking, a big chunk of Sunday, especially in the evening, to participate in this. I would just say I'm super grateful to Bano, of course, but I wanted to say even in a fancier way, I'm very grateful to Providence that brought us together with Bano long time ago at Berkeley, and that was the beginning of the friendship, and then and collaboration, and then Bano arranged for my first trip to India in 2005, which was an eye-opening experience to me in many, many, many ways. And so after that trip, I would tell all my friends, have you been to India? And then they say, no, I haven't been to India. And I say, well, I would say, you don't know how this planet works. You have to, if you want to have a full picture of all the amazing and diverse things that there are in this world, you have to enrich your experience by traveling to India. And I myself, as Bano said, don't miss an opportunity to do this. And so I have a lot of friends and a very, very nice scientific collaboration in India. So starting with Bano, number one, but then so Bano introduced me. But there's always some young people around around Banu, and so and these young people are getting you know less young now, the first ones that that I met, and so I'm super happy and grateful that I met Sadiq already in 2005, and this has been super interesting. And Sadiq came to Berkeley, as he said, and we had a lot of adventures together there, and also in India. And then we have a lot of common interest, and some of my research interests are definitely also influenced by Sadiq, and Sadiq has this way of looking at the problem and seeing the most important thing in it, as you have experienced yourselves by hearing his talk, which started with a wonderful tutorial. And then yes, so I've already said Banu is always surrounded by young people, and Vijaya and KVP Lata were the first people I met apart from Banu at the Indian Institute of Astrophysics. And yeah, I was looking at this huge supercomputer that Vijaya was showing in his talk, and I was remembering how he was very proud to show me in some back room some cluster that he himself actually I think put together at that time. And then Sadiq had a lot of students, and one of them, Arijit, was the one who traveled. My students went to India, as was mentioned. Victor, Andrew, Park, and Derek, and Arijit Sharma came to Berkeley, and he joined the dysprosium experiment. And I just would like to mention something, so you know about the important fact about Arijit, which is that nowadays dysprosium is one of the key systems in cold atoms, and people do BECs and study a lot of interesting physics in dysprosium because it has the largest, it's an atom with the largest magnetic moment in the ground state. So there are all kinds of condensed matter effects that are being studied. And some years ago, you wouldn't believe it, but people really had this notion that it's impossible to laser cool complex atoms. Okay, yeah, because the energy level structure is so complicated, there are so many levels and sublevels that it's impossible to cool. So one of the things that Arijit has done while at Berkeley is working with some other students in my group, specifically Nathan Leifer and others. He demonstrated for the first time that you can actually cool dysprosium. At that time, it was a cooling in an atomic beam, basically narrowing the velocity distribution. But that's the very first paper where dysprosium was laser cooled, and only several years later, people demonstrated that it can be trapped and even both condensed. So the other thing I wanted to say is that I'm an experimentalist, but I have been really blessed to interact a lot with theorists. Banu is one of them, but Banu's student Dilip also came to Berkeley on that program that Banu mentioned, and he really taught me a lot about how to think about atomic theory, and then later on, as you know, I visited Dilip in Ahmedabad, and we traveled around together and had a lot of adventures, both in terms of physics and, as you heard, otherwise. And this visit to the Zoroastrian priest was just one chapter. There are many chapters in our adventures. For example, the trip to the market and a visit to a famous Jewish Indian writer, Esther David, and many other things. All right. So then, Brajesh is a Dilip student, correct?
Yes.
So
Yeah,
so
correct.
now we see how it goes. Generation to generation. There is actually in Jewish tradition there is a expression, it's called dor vador, which means generation from generation. And so it's wonderful to see now yet another generation of students becoming such prominent scientists and reporting this fantastic work. And yes, and I must say I'm very impressed with the work that you guys do in India. And every country has special sort of conditions and some things that are easier in some countries than another, some things that are more difficult. But overall, there is wonderful variety and depth and enthusiasm towards science in different areas. And so the most recent introduction that Banu made to an Indian scientist was Tanmoy. And so this is yet another area. And I'm very happy about this contact. And also, there were Tanmoy mentioned Kasturi. She was at this program, and she really impressed me with her experiments that are at the highest world level in NV Diamond. So anyway, this is maybe all I have to say. That once again, I'm really grateful for your friendship, collaboration, and this symposium, which is a really precious, wonderful, and undeserved gift to me. Thank you.
Okay, so Dima, thank you very much. Okay, so thank you very much. And I'm sure, everybody will agree with me that, that we've learned a lot from you, and we will learn a lot from you in the future. And we all look forward to many more years of very productive interactions and collaborations with you. So thank you very much for all that you've done for us. Okay.
Thank you so much.
Okay. Does anyone want to say anything? I mean, or...
Yeah, I just want to add here that this was a very pleasant gathering of friends and colleagues, and probably we should aim for the 65th one 5 years from now.
Yes. Of course, yes.
I'd like to also add one thing that maybe I missed. The earlier, like points people may have talked about. So Professor Budkar just now mentioned that Professor VP students are getting older. So what I see is Professor Budkar is getting younger day by day. In the sense that every time whenever I see his research work, he tries to work something new. That is really remarkable. And the books he's writing, that really it helps of course it helps students, but it also helps young researchers like us. So that way I'd like to once again wish all the best, and also would like to wish him to write many more books and do good research in the years to come, and also of course good health to him and as well as to his family members. Thank you, Professor Budkar.
Hi, Dima. So this has been a very good experience to see all the people. And thank you for everything. It has been a very pleasant experience overall to have interacted with you. And I hope to interact with you in the future too, not only in science, but I admire your zest for life. And you are the ideal scientist who has a proper work life and everything else in life in a proper balance. So yes, I hope that, as Rizit has said, the 65th birthday is just 5 years down the line. So we look forward to another great occasion to celebrate the great works that you have done. And we have to see more of great works coming in the way. So Dima, it's been a great pleasure knowing you and being your friend, being your collaborator.
Yeah. Good. And the 65th birthday celebration will be in India, in person.
Why not?
Okay.
Why not? That will be great.
Yeah. Okay. All right. Okay, so
Okay, Dustin? Dustin?
yeah. Oh, hello. Yeah. Hi.
I'm okay. So, thank you very much for organizing a very nice symposium. And also, we thank Professor Buka. So, his very nice study for fundamental physics, especially the parity violation. And I also very surprised because many many presentation in the fundamental physics in India today. So, so very nice talks. So all speakers. Thank you very much.
Thank you.
But finally, so I have a question because you know the most of fundamental physics related to the precise spectroscopy. So because people try to measure the difference from the prediction due to the standard model. You know? So because people want to probe the new physics beyond the standard model. Oh,
Can you repeat the question? I didn't quite get the question. Okay, son.
Can you hear? Okay.
Yeah, we can hear, but I didn't understand the question.
Yes. For example, the parity violation is sensitive to the detect the dark matter. So then, people ask us, does dark matter exist inside the vacuum chamber? What do you know the answer?
Yes, I know the answer. And actually, before I answer that, I'd like to maybe take the opportunity. I see that one of our students, Malavika Unis, is here. I don't know, Malavika, do you have a camera? Can you maybe quickly? Yeah, there she is. So Malavika is a relatively new student in our group, and she's actually working on catching the dark matter that's in the vacuum chamber. Yes, she is a part of the Casper experiment, and so it depends actually on the type of the dark matter. So there are many. We don't really know what it is, and in some models it's like a field. So we are, for example, in this Casper experiment, we are looking for this pseudoscalar field, and that is supposed to basically be everywhere here in the galaxy. And it actually looks, the gradient of that field looks like a magnetic field. So we have a spin precession experiment. So there are magnetometer experiments, and Malavika is working actually on this nuclear magnetic resonance NMR experiment to catch it. So we're quite excited about it. But then there are other things. Then there are other things that can be. more about the magnetic shielding, for example. So there are some models in which this kind of field can be either screened or in some cases enhanced by the presence of the shielding. But in general, yes, there is dark matter around us. There is also, the other thing is, if maybe this is like an important point. So people think that dark matter could be some particles or fields beyond the standard model, and so to be sort of the dark matter, it has to exist in its real form. But if the particle exists in principle, it could also exist in virtual form, for example, as an intermediate boson, and then it will modify the usual interactions between normal standard model particles and lead to some forces that are beyond, the usual four fundamental forces, and this is called the fifth force. And we have a lot of work recently on looking for spin-dependent, actually both spin-independent and spin-dependent fifth force interaction, and this is actually in some way more powerful than search for dark matter, because these kind of experiments are sensitive to beyond the standard model physics, even if those particles we are going to detect this way are not the dark matter. So in some ways, these are more powerful.
Okay, thank you. So if the dark matter exists as a virtual boson, so probably this means if we measure the difference of the weak charge delta Q, so it is always shifted delta Q.
Right. So for instance, it was mentioned that when you measure the parity violation in a chain of isotopes, you should be sensitive to Z primes, the extra Z bosons that are very light. Okay, but also weakly coupled. So in principle, those particles could be dark matter as well, for example. So there is a very close connection between, with fundamental symmetry experiments and dark matter, I believe. There is one more aspect I would like to mention. These dark matter fields, they are predicted to be time dependent. They should be oscillating at the Compton frequency of the underlying particle, and this should actually modify the way we look for them. For instance, axions, one of the very popular pseudoscalar particles, they shouldn't use EDMs, PT violating EDMs. But in contrast to the EDMs, the usual EDM experiments are looking for, these ones will be changing in time very rapidly. We don't know, it's a Compton frequency of the axion, which we don't know. But for example, could be megahertz, gigahertz or something, and the experiments that are designed to measure for permanent EDM that is not switching will not see this. So you have to modify your experiment.
Okay, thank you. So, and I think recently some people also try to measure the not EDM. Maybe people want to measure the nuclear MQM, magnetic quadrupole moment.
Yeah.
What do you think? So this is also related
Sure.
to the dark matter?
Yes.
I don't know.
I think it was proposed for a long time as so one of the shift moment and MQM, etc. So these are magnetic quadrupole moment. These are all good things to look for, I believe.
Okay, thank you.
Pano, you are muted. Still somehow muted.
Yeah, sorry.
No, yeah.
Yeah. Okay, so is there any other thing that?
Can I ask one?
Yeah, please.
This is related to the kind of outlook for this NV center based sensing application. So in next generation sensing application, for example, which would be a better material in terms of, for example, diamond or silicon carbide or hexagonal boron nitride? None.
Nobody knows, and it probably depends on a specific application. So silicon carbide, people got very excited because there is more developed wafer mass production technology, for example, and hexagonal boron nitride is extremely popular recently also. But so far for actual sensing applications, I think it's nitrogen vacancy centers is still the leader, although there are some things, for instance, for instance, magnetic measurements at low temperatures and high fields where silicon vacancies may be better. And I think it's too early to kind of say who the champion is, and it's always good to have also different things. Because you never know what is the best for the application, the next application.
Right. Thank you. Thank you very much.
Okay. So if there are no more comments, we once again wish Dima all the very best and thank you for joining us, giving us a privilege to celebrate your 60th birth year, and all the very best to you always.
Thank you so much. Thank you so much once again.
Okay. Thank you. Okay. Bye.
Bye-bye.
Bye.
Bye.
Bye.